The AI industry runs on S-curves. Find a scaling axis, ride it until it flattens, then find the next one. The entire business model depends on the next curve existing. The first curve was parameters. Make the model bigger. Double the layers, double the attention heads, watch the benchmark numbers climb. GPT-2 had 1.5 billion parameters and could write coherent paragraphs, impressive for 2019 but limited. GPT-3 scaled to 175 billion, a 100-fold jump, and the results were genuinely shocking. Zero-shot learning worked. Feed it a prompt it had never been trained on, and it produced useful output. Summarization, translation, basic code generation, capabilities that previously required task-specific models emerged from raw scale. The research community watched a single model do the work of dozens of specialized systems. The scaling hypothesis looked like a law of nature. Make it bigger, unlock new capabilities. So the industry made it bigger and bigger. GPT-4 training run cost over $100 million, roughly 25 times what GPT-3 cost. Estimates put its architecture at well over 1 trillion parameters across a mixture of experts' design. Google spent comparable sums on Gemini Ultra. Anthropic trained Claude 3 at a similar scale. Meta released Llama at progressively larger sizes. Between 2020 and 2024, the cost of training a frontier model went from single-digit millions to 9 figures. The capabilities improved. GPT-4 is better than GPT-3, noticeably better at coding, better at following complex instructions, better at multi-step tasks. But it is not 25 times better, and it cost roughly 25 times more to train. The easy gains, coherence, fluency, basic instruction following, had already been captured by the previous generation. What remained was harder: reliable multi-step reasoning, factual consistency, genuine understanding of problems the model hadn't seen before. And those capabilities weren't responding to parameter scaling the way fluency had. You could double the parameters again, spend another 100 million, and get maybe 15 or 20% better performance on the benchmarks that actually mattered. Picture a graph. The x-axis is training cost, each tick mark a doubling of budget. The y-axis is capability. Early on the line shoots upward. A steep exhilarating climb, then it starts to bend, not crashing, not flat, bending, the slope decreasing with each doubling. Each dollar buying less capability than the last. Somewhere past 100 billion parameters. The second curve was data. If bigger models aren't delivering proportional gains, maybe the problem is starvation. Train them on more text, more data, cleaner data, broader coverage. Scrape the entire internet. License every book publisher willing to deal. Ingest every academic paper, every Reddit thread, every code repository on GitHub. This worked too. DeepMind's chinchilla paper showed that most frontier models were actually undertrained. You got more capability per dollar from training a smaller model on more data than from scaling parameters with fixed data. The industry pivoted. Data became the bottleneck everyone focused on. Labs started hoarding proprietary text. Licensing deals with news publishers and book distributors became the new arms race. Scaling story continued. The variable changed from parameters to tokens, but the curve still pointed up, until the well started running dry. And unlike parameters, this wasn't a problem you could throw money at. You can build more GPUs. You can't build more internet. The total stock of high-quality human-generated text on the internet is finite. It sits in the range of tens of trillions of tokens. The frontier labs are consuming this at an accelerating rate. Epoch AI published research estimating that we will exhaust the usable supply within a few years at current consumption rates, and the labs are consuming faster every quarter. The internet generates new text daily, but the ratio of signal to noise is brutal. Most new content is low quality. Spam, duplicates, SEO filler, and increasingly machine-generated text that contaminates the training pool from the inside. The proposed fix was synthetic data. Use your existing model to generate training data for the next model. Bootstrap the supply from your own outputs. The research on this is damning. Training on model-generated text introduces compounding drift. Each generation amplifies the biases and artifacts of the model that produced it. The distribution narrows. The tails get cut. Rare but important patterns, unusual legal precedents, non-obvious proof techniques. Edge case code constructs disappear first because they're statistically unlikely and the generative model smooths them out. After a few generations of recursive self-training, the model converges on a bland, mode-collapsed version of the original. Researchers call it model collapse. The data you generate is a pale photocopy of the data you actually need, and each copy gets paler. And each copy gets paler. So the industry did what the industry always does when a curve bends. It went sharping for a new one. The pressure to find that curve isn't academic. It's financial, and the numbers are enormous. Microsoft has committed over $13 billion to OpenAI. SoftBank announced a $100 billion infrastructure project called Stargate. Amazon invested $4 billion in Anthropic. Google has staked its core search business on Gemini delivering. Across the industry, the total capital committed to the premise that AI capabilities will keep scaling exceeds $500 billion. That capital demands a growth story. Investors don't write nine-figure checks for diminishing returns. Boards don't approve data center builds costing tens of billions for the curve is bending. The financial psychology here is straightforward and powerful. When you've committed hundreds of billions to a trajectory, you need that trajectory to continue. You don't need it to be proven, you need it to be fundable. You need a new axis, a variable you can point to on a slide and say, this is the next lever. This is where the growth comes from. In the second half of 2024, the industry converged on an answer. OpenAI released o1 in September, a reasoning model that spends extra compute at inference time, working through problems step by step before answering. Math competition scores jumped, coding benchmarks improved. 3 months later, o3 pushed even higher. Google shipped Gemini 2, zero flash thinking. DeepSeek released R1 in January 2025 and matched frontier reasoning performance at a fraction of the training cost. Anthropic introduced extended thinking in Claude. Within 6 months, every major lab had pivoted to the same narrative. The new scaling axis, test time compute, the mechanism driving it, reinforcement learning. Train the model to think longer and harder at inference time, and the performance keeps scaling with the compute you throw at it. The pitch was clean enough for an earnings call. We've found a new way to make models smarter. Instead of making them bigger, we teach them to think harder. The more compute you give them at inference time, the better they reason. The curve is going up again. Here's the story. Take your big pre-trained model, the one that already knows language, knows facts, can write code and summarize documents. Now teach it to reason. Give it a reward signal for solving problems correctly. Let it try different reasoning paths, see which ones reach the right answer, reinforce the successful paths. The model discovers reasoning strategies that no human explicitly programmed. It improves by practicing, the way a math student gets better by working through problem sets. Model that thinks, AI that reasons, System 2 thinking in machines. The marketing cooperates, the benchmarks cooperate, math scores climb, coding benchmarks climb, science reasoning scores climb. Quarter over quarter the numbers go up and the S-curve looks alive again. The results aren't fabricated. Reasoning models genuinely solve harder math problems than their base models. They produce better code on difficult programming challenges. They perform better on multi-step logic tasks. The improvement is real and measurable. But improvement and understanding are different claims. And the gap between them is where the entire bet breaks down. When a reasoning model solves a competition math problem, the mechanism underneath is still next token prediction. Each word is chosen based on what's statistically likely to follow the previous word, given a training distribution that included large volumes of mathematical reasoning text. The RL training didn't teach the model mathematics. It biased the model's sampling distribution toward token sequences that correlate with correct answers. It made the model more likely to walk down reasoning paths that led to verifiable solutions during training, and less likely to walk down every other path. The capability was already in the base model from pre-training. RL concentrated it. That sounds like a fine outcome, but the cost is hidden. By concentrating the model's probability mass on reasoning patterns that worked during RL training, The system simultaneously suppresses patterns that lead to correct solutions on problem types the training didn't cover. The model gets more reliable on familiar problems and less capable on unfamiliar ones. It trades breadth for consistency. On a benchmark that trade registers as pure improvement, pass rate goes up, the press release writes itself. For a system that needs to handle the full range of real-world problems, not just the ones in the training set, it's a narrowing trap disguised as progress. The model looks smarter. Its actual reasoning boundary has shrunk. This matters because the infrastructure is already being built. Data centers designed for RL training workloads. Custom silicon optimized for inference-time reasoning compute. Research teams across every major lab reorganized around reinforcement learning, hiring RL specialists, deprioritizing alternative approaches, reshaping their entire research agenda around one assumption: that RL is the path to general intelligence. The bet is specific. Optimize a reward function hard enough and understanding falls out. Give the model enough practice problems and it learns to reason. Scale inference-time compute and capability keeps climbing. That's the theory. And it's the theory that hundreds of billions of dollars are now riding on. If that theory is wrong, not slightly wrong, but architecturally wrong, then the industry is building the most expensive dead end in the history of technology. Not because the models won't keep improving. They will. The benchmarks will keep climbing. But the improvement ceiling is lower than people think, the failure modes are more dangerous than the benchmarks reveal, and the money is flowing toward a theory of intelligence that cannot produce what it promises. This video breaks that argument down across 4 independent failures: economic, engineering, architectural, and the modern mirage of reasoning models, where approximately half contained hallucination or spurious tokens. Then we turn constructive: world models, active inference, evolutionary strategies, and latent space reasoning that understands before it optimizes. By the end, you'll see why we built Irys on a completely different foundation, one that produces outputs you can trace, debug, and trust. We'll start with the simplest case against RL, the economics, because even before we question whether RL works in theory, it fails basic arithmetic. Let's start with cost, not theoretical cost, actual dollars and actual time. The AI industry loves to quote training time in days or weeks. We trained our agent in 10 days. That sounds fast, but the metric they bury, the one that actually matters, is experience consumed. How much simulated time did the agent need to learn its one trick? OpenAI 5 learned to play Dota 2 at a professional level. The training setup ran 256 GPUs and 128,000 CPU cores, playing the game at massively accelerated speeds. Every single day of training, the system accumulated 180 years of gameplay experience. The total, approximately 45,000 years of simulated Dota. Not 45,000 games, 45,000 years. Alpha Star needed roughly 200 years of real-time StarCraft 2 per agent to reach Grandmaster level. AlphaGo Zero burned through thousands of years of Go games. These are narrow, well-defined games with fixed rules, complete state observability, and deterministic physics. Now put that number in context. A human child learns to walk in about a year. A foal does it in minutes. A human learns the basic rules of Dota in a few hours and can play at a competent level in a few hundred hours. The RL agent needed 45,000 years to do what a teenager does in a summer. The RL agent needed 45,000 years to do what a teenager does in a summer. 45,000 years to do what a teenager does in a summer. not 45,000 games. Let me make that compute setup concrete, because large numbers numb you if you don't feel them physically. 256 GPUs means roughly 32 8-GPU servers. Each server weighs about 150 pounds and draws 5 to 10 kilowatts of power. 32 of them fill 4 to 6 standard data center racks, each rack about 7 feet tall, 2 feet wide, bolted to a raised floor with chilled air blowing up through perforated tiles. You can walk past them in about 15 seconds. They occupy the footprint of a small studio apartment. Now the CPUs, 128,000 CPU cores. A typical high-end server has about 128 cores. That's roughly 1,000 servers. 1,000 servers fill about 40 data center racks. Picture 4 rows of 10 racks each, stretching roughly 40 feet long and 20 feet deep. The cooling infrastructure alone, fans, liquid cooling loops, crack units pushing cold air under the floor, doubles the floor space. You're looking at a room the size of a basketball court, humming at 75 to 80 decibels, loud enough that operators wear hearing protection. The power draw on those 1,000 CPU servers runs somewhere between 400 and 700 kilowatts. Add the GPU cluster. Add cooling overhead, which typically runs 30 to 40% of the compute load. Total system power lands around 1 megawatt. That's enough electricity to power about 800 American homes. Running continuously for the duration of the training run. All of that infrastructure, all of that power, all of that engineering to teach one system, one game. A game with fixed rules, a fixed map, a fixed roster of characters, and a known strategy landscape. And it produced a system that can't play a different game. Not even a slightly different version of the same game. Not even the same game after a balance patch moves a number by 5%. When someone tells you that OpenAI 5 learned to play Dota, you need to understand what that word means in this context. Because it doesn't mean what you think it means. The system didn't learn what a tower is. It didn't learn what winning means in any transferable sense. It didn't develop a concept of strategy, teamwork, or game theory. What it did was memorize probability distributions over billions of microstates through brute force sampling. It correlated input patterns with reward signals until the correlations were dense enough to beat humans at that specific game, in that specific engine, with those specific rules. Change the map, change the character raster, change the visual style. Apply a major patch the way any live game does, and the entire 45,000 years of experience becomes worthless. The agent doesn't adapt, it shatters, because it never understood anything. In effect, the system built an extremely expensive statistical model that approximated a lookup table within its training distribution. And this isn't unique to games. In robotics, researchers at Berkeley trained an RL agent to pick up a cup and pour water into another cup. The training ran in simulation for the equivalent of several hundred years of robot time. The agent learned to pour in that exact simulator, with those exact cup dimensions, that exact water viscosity model, that exact lighting condition. Move the target cup 2 centimeters to the left in the real world and the agent misses. Change the cup from plastic to ceramic, different weight, different friction coefficient, and the grasp fails. The lighting in the real lab differed from the simulator by enough to confuse the vision pipeline, and the robot reached for a shadow instead of the handle. Several hundred years of simulated experience. 1 cup, 1 pour, non-transferable. In tool use, the pattern repeats. RL agents trained to call APIs learn the exact function signature, the exact parameter order, the exact error codes of the version they trained on. When the API provider ships a new version, renames a parameter, changes a default, deprecates an endpoint, the agent doesn't read the changelog and adapt. It calls the old endpoint, gets a 404, and retries the same call in a loop because read documentation and figure out what changed wasn't in the reward function. It memorized the old answer. It never understood the question. A junior developer handles an API migration in an afternoon, They read the diff, update the calls, test. The RL agent, trained at immense cost on the old version, has to be retrained from scratch on the new one. The old training is wasted. Every dollar spent learning the V2 signature buys exactly 0 capability on V3. Every RL deployment story follows the same plot. Spend millions to train. Deploy into a world that moves. Watch the agent break on a change that any human handles without thinking. This is exactly why Irys doesn't train per task it retrieves from structured memory, so a new document type or contract variation doesn't require retraining anything. The RL faithful have an answer to this. They'll tell you the sample inefficiency is actually a feature, not a bug. The whole point of AlphaGo 0 was that it learned from scratch. No human data, no human biases, pure self-play, tabula rasa, the blank slate figuring everything out from first principles. This is the most successful marketing campaign in AI research history, and it doesn't hold up. Let's walk through what starting from scratch actually means. Mechanistically, when you initialize a neural network, every weight starts as a small random number, drawn from a Gaussian distribution, usually with a standard deviation scaled to the layer width so activations don't explode or vanish on the first forward pass. These random weights define the agent's initial policy, its starting map from observations to actions. What does a random policy do in Dota 2? It moves the character in random directions. It attacks random targets. It uses abilities at random times on random tiles. It buys random items from the shop. It walks into enemy towers and dies. The behavior is indistinguishable from a player mashing buttons with their eyes closed. From this starting point, the agent has to discover, through reward feedback alone, that towers hurt you, that enemies kill you, that gold buys items, that items make you stronger, that killing creeps gives gold, that last hitting creeps gives more gold than standing nearby, that different heroes need different item builds, that team composition matters, that map positioning matters, that objectives have timing windows. Every single concept, from don't stand in the fire to coordinate a 5-man team fight at the 30-minute Rasian spawn, has to be rediscovered from random noise through billions of trial and error episodes. AlphaGo 0's no human data claim held for Go, a game with simple rules and perfect information. But when DeepMind scaled to StarCraft with Alpha Star, pure self-play failed. They had to add human replays, curriculum learning, and reward shaping. Alpha Star's actual training pipeline starts with supervised learning on human game replays, then uses RL on top of that foundation. The Tabula Rasa story works for board games with tight rule sets. It collapses the moment the environment gets complex enough to matter. Now compare this to a human. A 12-year-old sits down to play Dota for the first time. Before touching the keyboard, they already know things that look dangerous probably hurt you. Resources buy upgrades. Teammates are allies. Enemies have goals opposed to yours. Buildings belong to somebody. Moving toward the enemy base is risky. Red visual effects probably mean damage. Green ones probably mean healing. None of these come from Dota. These are priors, causal models of the world built over 12 years of living in physical and social reality, compressed into the kids' neural architecture before they ever saw a loading screen. Now compare to a foal. A horse is born. Within 2 to 5 minutes it pushes itself upright on wobbly legs. Within an hour it walks. Within a day it runs alongside its mother at 15 miles per hour. The foal isn't learning from scratch. Its motor cortex arrives pre-wired. Millions of years of equine evolution tested trillions of neural configurations for quadruped locomotion. The architectures that encoded effective central pattern generators, the spinal circuits that coordinate the timing of leg flexion, extension, weight transfer, and balance correction, survived to reproduce. The architectures that didn't died before reproducing. The foal's nervous system at birth already contains a nearly complete locomotion controller, refined over roughly 55 million years of evolutionary selection. Those first minutes of stumbling aren't learning to walk, they are calibration. The controller is adjusting to this specific body's leg length, weight distribution, hoof grip on this specific ground surface. The algorithm is already there. The parameters are being tuned. Evolution didn't learn from reward signals. It ran a population-based architecture search across hundreds of millions of years and billions of individuals, and baked the winning architectures into the genome. The foal's neural wiring is the compressed output of that search. It's not tabula rasa, it's the opposite of tabula rasa. It's the most heavily pretrained system in nature. RL's ideological commitment to blank slate learning means it has to rediscover physics from pixel correlations. Every single time a random initialization has no concept of gravity, no concept of solid objects, no concept of other agents having goals, no concept of cause and effect. It's not even wrong about these things, it has no representation of them at all. The learning problem isn't refine existing knowledge. It's construct all knowledge from scratch, using one scalar number per episode as your only feedback. That's why it takes 45,000 years. The information bottleneck, one reward signal per episode, forces the system to extract structure at an absurdly slow rate from an absurdly low bandwidth channel. Evolution solved this by running billions of parallel experiments over geological time and encoding the results structurally into DNA. RL tries to match that outcome with a single agent and a single lifetime of trial and error. The math doesn't close. Irys starts with the priors baked into the base model during pre-training. Robotics is where RL's sample inefficiency crashes into physical reality. You can't run a physical robot for 45,000 years. Motors wear out after thousands of hours. Joints accumulate backlash. Gears strip. The robot itself costs $50,000 to $500,000 depending on the platform, and every hardware failure means downtime, replacement parts and recalibration. So the standard approach is, train the policy in simulation, then transfer it to the real robot. This is called sim-to-real transfer. It almost never works cleanly. The problem is the reality gap. A physics simulator models the world with equations, rigid body dynamics, friction coefficients, contact forces, actuator response curves. But these equations are approximations. Real friction isn't a single number. It varies with surface texture, temperature, humidity, dust, and wear. Real actuators don't respond the way a first-order differential equation says they should. They have latency that varies with temperature, backlash that depends on direction of motion, and nonlinear torque curves that differ unit to unit even from the same manufacturing batch. Real lighting changes minute to minute as clouds move, as overhead fluorescents flicker at 60 Hz, as someone walks between the robot and the window. An RL agent trained in simulation overfits to the simulator's specific approximations the way it overfits to everything else. It learns policies that exploit the simulator's physics model, exactly the way CoastRunners exploited the game's scoring system. Transfer that policy to a real robot, and the subtle differences between simulated friction and real friction cause the gripper to slip. The mismatch between simulated motor response and real motor response causes overshoot. The policy that worked flawlessly across 1 million simulated episodes fails on the first physical trial. The standard patch is domain randomization. During training, you randomize the simulation parameters. Vary the friction between 0, 3 and 0, 8. Vary the object mass by plus or minus 20%. Vary the lighting angle. Vary the actuator delay. The idea is that if the agent succeeds across a wide distribution of simulated environments, it'll handle the real one because reality is just another sample from that distribution. Domain randomization helps. It doesn't solve the problem. You're still guessing which parameters to randomize and what ranges to use. Miss a parameter, say you randomized friction and mass but forgot air resistance, or you randomized actuator delay but not actuator backlash, and the transfer still fails. Set the range too narrow and reality falls outside it. Set the range too wide, and the agent learns an overly conservative policy that barely functions anywhere because it's trying to be robust to everything simultaneously. And it gets worse over time. A robot deployed in a warehouse doesn't face a static environment. Boxes arrive in different sizes, shelves get rearranged, forklifts change the layout, a spill changes the floor friction, seasonal temperature shifts change actuator behavior. The policy was trained against a frozen distribution and the real world drifts continuously. Every day the robot runs, the gap between its training distribution and reality grows. The only response RL offers is retrain. Pull the robot offline, spin up the simulator, burn another few thousand GPU hours, redeploy and wait for the next drift. Compare this to a human warehouse worker. A new box shape shows up. The worker looks at it, adjusts their grip, lifts it. No retraining, no simulator, no GPU hours. The worker has a causal model of objects, weight and grip that generalizes instantly to novel situations. RL has a lookup table that shatters the moment the input moves outside the training distribution. The sim-to-real gap is just a specific instance of RL's general inability to handle distribution shift. The same gap that kills a game-playing agent when the patch notes change kills a robot agent when the real world doesn't match the simulator. And the real world never matches the simulator. That's what real means, so let me pull the thread so far. RL burns 45,000 years of experience for one game. It can't transfer that knowledge to a different game, a patched version, or even a different lighting condition. The sim-to-real gap means laboratory results don't survive contact with deployment, and every one of these problems traces back to the same root. RL memorizes correlations within its training distribution instead of building transferable models. Now let's put a price tag on what that means for general capability. Now do the arithmetic the AGI optimists won't do. Each documented RL success, OpenAI 5 for Dota, Alpha Star for StarCraft robotic manipulation tasks, consumed enormous compute budgets for a single narrow skill. Boston Dynamics spends hundreds of millions per year on locomotion alone, and they don't use end-to-end RL because they know the economics collapse. A human adult has thousands of distinguishable skills, not just walking and talking. Skills like estimating whether a container will hold a liquid by looking at it, adjusting grip force based on an object's predicted weight before fully lifting it, reading a room's social dynamics within 3 seconds of entering, knowing that the person who just asked is everything okay, probably noticed something wrong, parsing sarcasm, packing a suitcase so the fragile items don't break, finding your way through an unfamiliar building by reading signage and inferring floor layout from the elevator numbering scheme. Each of these skills, in RL terms, is a separate training problem, a separate reward function, a separate environment, a separate massive compute bill. If each skill costs millions and none transfers, the aggregate cost is prohibitive, and each new skill adds linearly to the total because nothing learned in one domain carries to the next. But human skills compose. You combine walking with carrying with route finding with talking with monitoring your grip strength, with tracking the position of other people around you. RL can't compose skills because each skill is a separate policy trained in a separate environment with a separate reward function. There's no shared representation underneath. The weights encoding walk forward have nothing in common with the weights encoding carry object. They are stored in different networks trained on different reward landscapes. There's no mechanism for merging two policies into one that does both things simultaneously. You'd have to train the composition from scratch. A new environment, a new reward, another massive compute bill, and then the environment changes. New API version, new office layout, new teammate with different communication patterns. Retrain, the old investment is gone, the meter resets to zero. There's a reason no company on Earth has built a general-purpose RL agent despite decades of research and billions of dollars of cumulative investment. The per-skill economics make it structurally impossible, not impractical. Impossible. The cost scales linearly with skill count, the skills don't compound, and the investment depreciates the moment the environment shifts. A child learns to pour water once. That skill transfers to pouring juice, pouring sand, pouring beads, pouring batter into a pan. The underlying model, tilt the container, gravity moves the contents, control the angle to control the rate, generalizes because the child built a causal model of pouring, not a lookup table mapping one specific cup orientation to one specific motor sequence. RL doesn't build causal models. There's a recent finding that crystallizes this problem in the domain where RL is supposed to be working best right now. Language model reasoning. Researchers studying reinforcement learning from verifiable rewards, RLVR, the technique used to train reasoning models like DeepSeek-R1 and OpenAI's O-series, discovered something the industry hasn't fully absorbed. As RLVR training progresses, pass at 1 improves. The model's first attempt gets the right answer more often. This is the number that goes on the benchmark. This is the number that gets reported. This is the number that makes the model look smarter. But pass at 256, the fraction of problems the model can solve if given 256 independent attempts decreases. The reasoning boundary shrinks. Let me walk through what that means with a simplified illustration, because the mechanism is severe. Imagine a base model that scores pass at 1 of 40% on a math benchmark. It gets the right answer on its first try 40% of the time. But if you give it 256 independent attempts at each problem, 256 rolls of the dice, pass at 256 sits at 95%. The model can solve 95% of the problems. The knowledge exists somewhere in its weights, encoded during pre-training. It just doesn't reliably surface on the first try. The correct reasoning path is in there, but it competes with many other paths, and on any single sample the model might walk down a wrong one. After RLVR training, pass at 1 climbs to 60%. The benchmark number looks great, press release written, blog post published, Twitter thread goes viral, but pass at 256 drops, say from 95 to 80%. The model has lost the ability to solve problems it could previously solve. Those reasoning paths, valid, correct paths to correct solutions, were suppressed, pushed below the sampling threshold, effectively deleted from the model's behavioral repertoire. Here's what's happening mechanistically. RL increases the probability of actions that earned high rewards and decreases the probability of actions that earned low or zero rewards. A reasoning path that reaches the correct answer through an uncommon approach, a path that works but isn't the highest scoring path averaged over the training set, gets its probability reduced. Not because it's wrong, because a different path scored higher more consistently. Over thousands of training steps, these alternative correct paths get their probabilities ground down until they fall below the effective sampling threshold. Given 256 tries, they still wouldn't fire. They are gone. Picture a probability distribution over reasoning paths. Before RLVR, the distribution is wide and bumpy. The peak is moderate, the most common path fires with middling probability. But the tails are thick, carrying hundreds of alternative approaches, many of them correct for specific problem types. After RLVR, the peak shoots up. The tails flatten and shrink. The alternative paths, labeled / rare but correct / drop below the noise floor. The model gets more reliable on the problems RL trained on and less capable on everything else. The pass at 1 improvement is real, but it was purchased by amputating reasoning diversity. The model isn't smarter, it's narrower. And narrowness in a system that needs to handle the full breadth of real-world problems is a loss dressed up as a gain. For a math benchmark, this might seem acceptable. You trade coverage on obscure problems for reliability on common ones. But legal reasoning isn't a math benchmark. A contract dispute might hinge on an unusual clause interaction that the model's rare but correct reasoning path would have caught. A patent analysis might require an unconventional chain of inference that the RLVR-trained model can no longer produce. The amputated tails contained exactly the kind of unusual, creative, correct reasoning that hard problems demand. This is RL's core dynamic, playing out even in its best-case modern application. RL doesn't add capability. It redistributes existing capability from breadth to depth. It takes a model that can solve many things unreliably and turns it into a model that solves fewer things more consistently. The benchmarks measure the consistency. They don't measure what was amputated. Irys's judge-guided search preserves that diversity. It generates multiple candidate paths and evaluates each independently. So a rare but correct reasoning chain survives as long as it passes verification. Here's why this matters for how we build real systems. Irys doesn't try to discover legal reasoning from scratch through tens of thousands of years of simulated depositions. It doesn't spend millions training an agent to understand one contract type that can't generalize to another. Irys stores structured knowledge in matter memory. It's a typed, relational knowledge structure. A matter isn't a blob of text dumped into a vector database and retrieved by cosine similarity. A contract clause is stored with its clause type, indemnification, limitation of liability, force majeure, along with its modifying conditions, its exceptions, its jurisdictional scope, and its explicit relationships to other clauses in the same agreement. A legal precedent is stored with its holding, the factual basis that produced that holding, the court that issued it, the jurisdictions it binds, and the subsequent cases that narrowed, expanded, or distinguished it. These aren't tags. They're typed relational edges in a structured knowledge graph. When a new query arrives, does this indemnification clause survive termination? Irys doesn't start from zero and try to rediscover contract law through trial and error. It retrieves the relevant clause from matter memory by type. It follows the typed relationships to the termination provisions in the same agreement. It checks whether the survival language is explicit, implied by the clause type, or silent. It pulls the relevant case law on implied survival clauses in the applicable jurisdiction, filters by recency and court hierarchy, and assembles a structured answer from existing knowledge with full provenance tracking. The learning already happened. It happened during pre-training, where the model absorbed the structure of language, law, and logic through millions of bits of signal per forward pass. Not one bit rewards, but the rich, high-dimensional structure of actual legal text. The organization happened when knowledge was ingested into matter memory with typed relationships and tracked provenance. The reasoning happens at query time through judge-guided latent search, generating candidate reasoning paths, evaluating them against multiple independent verification criteria, pruning the paths that fail, and committing only the survivors. The cost difference isn't incremental. It's categorical. Compare what it costs to teach RL a new skill versus what it costs to add a new document type to Irys's matter memory. RL needs a new reward function, a new training environment, and millions of dollars of compute, and the result doesn't transfer to the next skill. Irys needs an ingestion step that parses the document into typed relational structures, links it to existing knowledge within the authorized matter or organization boundary, and makes it available for retrieval. No retraining, no new reward function, no compute bill that scales with the complexity of the task, and the knowledge compounds within the access-controlled scope of each matter or organization. Every new precedent linked to existing clauses increases the system's effective coverage without retraining anything. The knowledge base grows and gets more connected over time, with provenance and access controls preserved. That's the opposite of RL, where each new skill is an isolated expenditure that contributes nothing to the next skill and depreciates the moment the environment changes. If this kind of deep dive into what's actually happening under the hood of AI systems is useful to you, subscribe and like. We go deep on the mechanisms, not the hype. The economics tell you RL can't afford general intelligence. But cost alone doesn't kill a technology if the results justify the price. Plenty of expensive technologies survive because they deliver when it matters. So the next question is, forget the price tag. When you do pay those millions, when you burn those 45,000 simulated years, what do you actually get? An agent you can deploy, maintain, and trust. The answer turns out to be an engineering nightmare that makes the cost problem look mild. So you pay the price. Your RL agent learns its one narrow trick. Now you have to deploy it, ship it, maintain it. And this is where RL systems reveal their second problem. They aren't just expensive, they are unreliable, not as a bug, as a feature of how they work. Run the same RL algorithm twice. Same code, same hyperparameters, same environment, different random seed. You get two completely different agents. I need to explain what a seed actually is because it sounds like a minor detail and it's the opposite of minor. A neural network starts training with random weights. Before the agent takes its first action, before it sees its first reward, someone has to initialize those billions of floating point numbers to something. You can't start at zero, the gradients would be symmetric and the network would never differentiate its neurons. So you draw from a random distribution. A Gaussian typically means zero-sum variance. The random seed is the number that initializes that random number generator. Seed 42 produces one set of starting weights. Seed 43 produces a different set. The differences are tiny fractions of a percent in each weight, noise level differences. Those noise level differences compound. Here's why. RL training is a feedback loop. The agent acts, the environment responds. The agent updates its weights based on the reward. Those updated weights change its next action, which changes the environment's response, which changes the next update. Each update depends on all prior updates, and each prior update depended on the one before it. The whole trajectory is path-dependent. A slightly different starting point produces a slightly different first action, which produces a slightly different first reward, which produces a slightly different first weight update, and by step 10,000 the two agents are in completely different regions of the weight space, pursuing completely different strategies. Henderson et al. Tested this systematically across the standard RL algorithms, PPO, TRPO, DDPG, the algorithms powering most of modern RL research. They ran each algorithm on each benchmark environment with multiple seeds. The variance was staggering. On some environments, the performance spread across seeds was larger than the performance difference between algorithms. Think about what that means. The choice of random seed matters more than the choice of algorithm. The noise in your initialization dominates the signal from your engineering. Specific numbers. On the Harper locomotion benchmark, one algorithm's performance across seeds ranged from near zero to near optimal. Same code, same hyperparameters. The difference between a champion and a catastrophic failure was a single integer passed to a random number generator. The research community knows this. The training trajectory is chaotic in the mathematical sense, sensitive to initial conditions in ways that cannot be predicted, explained, or controlled. You can't look at seed 42 and say here's why it worked and look at seed 43 and say here's why it didn't. Here's what that means for deployment. Training variance means you can't validate against a specification. You don't know which behavioral envelope you're deploying because each training run produces a different one. You can't guarantee that the agent you tested is behaviorally equivalent to the agent you ship, even if the code and data are identical. And when the deployed agent fails, you can't reproduce the failure for debugging, because retraining with the same configuration produces a different agent with different failure modes. A frozen, deployed policy can be deterministic at inference. The same input produces the same output. But you can't verify that the policy satisfies your requirements because the training process that produced it is non-reproducible. Traditional software engineering lets you write the same code, run it twice, and get the same result. RL can't clear that bar at the training level, and the training level is where the behavior is defined. Irys produces the same output for the same input. The reasoning trace is deterministic and auditable. There is no training variance to contend with because the reasoning architecture doesn't retrain per query. Even if you get a lucky seed, your agent is the champion, not the failure. The resulting agent has the structural integrity of a sandcastle. There's a perfect experiment that demonstrates this. Researchers trained a superhuman fighting agent through millions of rounds of competitive play. The agent could beat any opponent it was trained against. Impressive performance metrics across the board. Then an adversary learned to simply fall on the ground and wiggle its limbs in a bizarre, spastic dance. The superhuman agent had never seen this during training. It was an out-of-distribution input. Its policy collapsed. It flailed, confused, and lost. The adversary, which never even stood up, won 86% of episodes. A superhuman agent, millions of training rounds, beaten by an opponent doing the equivalent of lying on the floor. This pattern repeats everywhere RL meets the real world. RL policies collapse under distribution shift, the gap between what the agent trained on and what it encounters in deployment. Sim-to-real transfer is the most documented case. A policy trained in simulation exploits the simulator's specific physics approximations, and when deployed on a physical system, the subtle mismatches between simulated and real dynamics cascade into failures the agent has no response to. In deployment, reward hacking compounds the problem. Agents discover that gaming the measurement apparatus is easier than performing the task, and these gaming strategies only surface under real-world conditions the training distribution didn't cover. Drone flight control agents trained in simulation transfer to the real world and immediately veer into walls. The sim had clean textures, consistent lighting, no wind gusts. The real world has shadows that change shape, reflective surfaces that confuse depth sensors, and air currents that shift the drone's position between sensor readings. The agent learned to fly in a world that doesn't exist, and when it encounters the world that does, its policy collapses. Robotic manipulation tells the same story. An RL-trained robot arm learns to grasp a red cup on a white table, move the cup to a patterned tablecloth, and the grasp rate drops by half. Change the cup to blue, and it drops further. Add a second object nearby, and the arm freezes or grasps the wrong thing entirely. The agent didn't learn to grasp. It learned to correlate a specific visual pattern, red blob, white background, specific position, with a specific motor sequence. Change any variable and the correlation shatters. This is the central failure of the entire paradigm. The agent does not learn the concept of fighting, driving, flying, or grasping. It memorizes a high-dimensional lookup table. If my sensors read X, I do Y. When the sensors read something outside that table, the lookup returns nothing, and the agent's behavior becomes random. Or worse, confidently wrong. Irys's structured knowledge retrieval operates on typed objects, not raw pattern matching, so document format changes don't collapse the pipeline. The next three problems, distributional fragility, catastrophic forgetting, and the testing gap, are properties of all deep neural systems, not RL alone. Irys's own judges and retrievers are neural networks subject to the same constraints. But RL makes each one worse for three specific reasons. The policy changes with every training run, so the failure surface is never stable. The reward function creates optimization pressure toward exploits, so failures aren't random but adversarial, and end-to-end training means there are no modular boundaries to contain a failure in one component, from cascading through the entire system. I keep saying out of distribution, and that phrase deserves a mechanical explanation. What actually happens inside a neural network when it encounters an input it hasn't trained on? During training, the network sees millions of inputs. Each one produces a pattern of activations across its layers. Some neurons fire strongly, some weakly, some not at all. Over time, the weights adjust so that similar inputs produce similar activation patterns, and the output layer maps those patterns to correct actions. The network carves the input space into regions. Within each region, it has a learned response. Here's the problem. The network doesn't know where its regions end. It has no concept of a boundary. A standard neural network doesn't output a confidence score that means what you think it means. It outputs a softmax distribution, a set of numbers that sum to 1. Those numbers are often called probabilities, but they are not calibrated probabilities. They are relative activations pushed through an exponential function. A network can output 99.9% confidence on an input it has never seen anything like, because the softmax just picks the largest activation and makes it look dominant. So when an out-of-distribution input arrives, say a self-driving car encounters a construction zone with orange cones, flashing lights, a human waving a flag, and a lane pattern it's never trained on, the activations don't go to zero. They don't produce a I don't know signal. The input still flows through the network, still triggers some neurons, still produces some activation pattern. But that pattern doesn't correspond to any meaningful region the network learned during training. It's an accidental activation, a ghost pattern, and the network maps it to whatever output happens to sit closest in its weight space. The result is an action chosen with high confidence that has no relationship to the correct action. The car might accelerate because the ghost pattern accidentally resembles a green light, or it might turn left because the flashing orange activates neurons that also respond to turn signals. The failure is silent, no error code, no exception, no warning. The system does the wrong thing and reports that it's certain. This is why RL agents are interpolation engines. Between training points, they can blend and generalize reasonably. Outside the training distribution, they extrapolate along whatever gradient their weights happen to encode, and that gradient points nowhere meaningful. So your lucky seed brittle agent has failed in the wild. Something went wrong, now you have to fix it. Let's walk through the mechanics of why this is worse than it sounds. Your deployed RL agent fails on a new scenario, you need to fix it. In traditional software you find the bug, fix the logic, redeploy. The fix is local, understandable and testable. In RL you stare at a matrix of 10 billion floating point weights. The knowledge is distributed across billions of parameters, in a way that no human can read or trace. You can't patch a neural network. Your only option is to retrain, adjust the reward function and run the training loop again. The mechanism is well documented in sequential learning research. When you update weights to improve on new data, performance on old data degrades. The rate of degradation depends on how much the new objective conflicts with the old one. The weights are shared across all learned behaviors. There are no separate knobs for separate concepts. When gradient descent adjusts weights to improve one behavior, it changes the same weights that encode other behaviors. Techniques exist to mitigate this: experience replay, regularization, modular heads, but they reduce the rate of forgetting rather than eliminating it, and each adds complexity and compute cost. This is catastrophic forgetting. You retrain to fix one failure mode and the weight changes degrade other behaviors. You fix the regression. That introduces a new one. You're trapped in a regression cycle. Each fix touches shared weights and shared weights encode everything. There is no isolation, there is no modularity, there is no locality. You aren't engineering a system. You're playing whack-a-mole with a black box that costs a fortune every time you swing. Compare this to how engineers debug traditional software. A bug appears in production. You get a stack trace, a record of exactly which function called which other function, in what order, with what arguments, leading to the failure. You can set breakpoints and step through the code line by line. You can inspect every variable at every point in execution. You can write a unit test that reproduces the exact failure in isolation. You can fix the bug in one function without touching any other function. You can prove the fix works by running the test. You can prove it doesn't break anything else by running the full test suite. The entire process is local, traceable, and verifiable. Now try that with an RL system. Your agent does the wrong thing. Where's the stack trace? There isn't one. The decision flowed through 10 billion weights in a single forward pass, a matrix multiplication that took milliseconds. There are no function calls to trace. There are no variables to inspect. There's a tensor of activations at each layer, and no human can look at a tensor of thousands of floating point numbers and identify which dimensions contributed to the decision. Where's the unit test? You can test at system boundaries. Does the agent produce the right output for a known input? But you cannot enumerate the input space or prove behavioral properties. In traditional software, a unit test isolates one component and verifies one behavior. The internal representations of a neural network don't decompose into testable units the way functions do. Whereas the isolated fix doesn't exist. Every weight connects to every other weight through the graph. You can't change one behavior without risking all behaviors. There's no function boundary, no API contract, no interface that separates cyclist detection from stop sign recognition from lane following. It's one undifferentiated mass of parameters. Traditional software has decades of tooling built around a simple property. Code is readable. A human can look at a function and understand what it does. Neural network weights are not readable. No human, no matter how expert, can look at a column of 10 billion floating point numbers and say this is where the car learned to stop at red lights. You can build visualization tools, activation maps, gradient attribution, attention heat maps. They show you which inputs the network paid attention to. They don't tell you why. They don't tell you what the network would do with a different input. They don't give you a causal model of the decision. They give you a blurry shadow of a process that happens in a space no human can read or trace. This brings up a problem that the RL community rarely talks about honestly. How do you test an RL system? In traditional software, testing works because the input space is structured. A function takes defined types. You can enumerate edge cases. You can write specifications that say given input X, output must be Y. You can use property-based testing to generate random inputs within the type constraints and verify invariants hold. You can achieve code coverage, a measure of which execution paths your tests exercise. You can prove properties about programs formally, mathematically with guarantees. These methods are incomplete, statistical, and coverage-limited for RL systems. You can test at system boundaries, but you cannot enumerate the input space or prove behavioral properties. The input space is continuous and effectively infinite. A self-driving car's input is a tensor of pixel values from multiple cameras, plus LiDAR point clouds, plus radar returns, plus GPS coordinates, plus speed and acceleration vectors. The number of possible inputs is larger than the number of atoms in the observable universe. You can't enumerate them. You can't sample them representatively. Any test suite, no matter how large, covers a measure zero fraction of the space. You can't write specifications. What does drive safely mean as a formal spec? Don't hit anything. The car would never move. Obey all traffic laws. Traffic laws conflict with each other in edge cases. A construction worker waves you through a red light. Maintain a safe following distance. Safe is context dependent. 2 seconds on a dry highway, 4 in rain, 8 on ice, something else entirely when the car ahead is a motorcycle versus a semi-truck. The specification space is as complex as the real world, which means the specification is as hard to write as the intelligence you're trying to test. You can't prove properties. Formal verification of neural networks is an active research area, but the state of the art can verify simple properties. The network never classifies a stop sign as a speed limit sign on tiny networks with hundreds of neurons. Scaling to billions of parameters is computationally intractable. The verification problem is NP hard in the general case. There's no shortcut, so what do companies do? They run the agent in simulation and count failures. But the simulation has a distribution. The test results tell you the agent works within that distribution. They tell you nothing about the real world, which has a different distribution. And the gap between simulation and reality, the sim-to-real gap, is where the failures hide. You're left with a system that you can't specify, can't enumerate, can't formally verify, and can't test representatively. The only way to know if it works in the real world is to deploy it in the real world, and when it fails, you can't debug it. This is not an engineering process. This is hope. Irys' modular architecture, retrieval, candidate generation, judge evaluation, provides defined interfaces that can be tested and validated independently. The way Waymo tests its perception module separately from its planning module. This is why the companies doing the hardest real-world deployment work don't rely on end-to-end RL. Look at what Waymo actually ships. The driving stack is not a single neural network that takes pixels and outputs steering commands. It's a modular pipeline. A perception module identifies objects, cars, pedestrians, cyclists, signs, using neural networks that do one specific thing each, and can be tested and validated independently. A prediction module forecasts where those objects will be in the next few seconds, using physics-based models constrained by road geometry. A planning module computes a trajectory, using optimization methods from control theory with hard safety constraints that cannot be violated regardless of what the learned components suggest. And a rule-based safety layer sits on top of everything, enforcing absolute invariance. Never exceed this speed, never cross a double yellow line, always yield to emergency vehicles. Each module has a defined interface. Each module can be tested in isolation. When the car makes a mistake, engineers can identify which module failed and fix it without retraining the entire stack. If perception misclassified a cyclist, you fix the cyclist detector. The planning module and the safety layer don't change. The fix is local, verifiable, and safe. Boston Dynamics does the same thing with its robots. Atlas doesn't learn to walk through end-to-end RL. The locomotion controller uses model predictive control, a method from control theory where a physical model of the robot simulates trajectories forward in time and selects the best one, hundreds of times per second. The physical model encodes that gravity pulls down, that legs have maximum torque, that the center of mass must stay over the support polygon. These are hard constraints, not learned correlations. They don't forget, they don't drift. They work the first time and the millionth time because they encode physics, not statistics. RL enters the Boston Dynamics stack in narrow, bounded ways, for optimizing gate parameters, for adapting to terrain variations, always wrapped in safety constraints from the control theoretic core. The RL component can explore within a sandbox. If it produces a dangerous command, the safety layer overrides it. The RL never has full authority. It's a tuning mechanism, not the decision maker. This is the pattern every serious deployment follows. Use RL where it helps, constrain it with engineering that you can verify, and never give the learned component unsupervised authority over anything that matters. The companies building the hardest systems in the world already know what the benchmarks are hiding. RL is not ready to be trusted. It may never be ready in this form. We've covered 2 of the 4 cases against RL. The economic case showed that RL is computationally insolvent. 45,000 years of experience for one narrow game, with 0 transfer to any other task. The cost per skill makes general intelligence arithmetically impossible. The engineering case has shown that even when you pay that cost, the system you get is unreliable, irreproducible, fragile to novel inputs, and resistant to the debugging and testing methods that engineering depends on. The companies building the hardest real-world systems have already figured this out and built around RL's limitations with modular architectures, control theory, and hard safety constraints. Those are the cost and the symptoms. The next question is the deepest one. Why? Is RL unreliable because the algorithms need more work, or because the entire paradigm is pointed in the wrong direction? RL can't be stable because it's built on the wrong abstraction. A scalar reward is trying to capture a world with dimensionality, structure, causality, and constant drift. The brittleness isn't incidental. It isn't a bug that better engineering will solve. It's the inevitable result of using a tool that compresses the world's complexity into a single number and then tries to reconstruct that complexity through trial and error. The economic case tells you the cost. The engineering case tells you the symptoms. But neither explains why RL is architecturally limited. For that, we need to go deeper into the mechanism itself. Every Irys reasoning step is logged and traceable. Let me walk through what that means concretely. A law firm uses Irys to analyze a commercial lease. The system's conclusion is wrong. It says the tenant has no early termination right, when in fact there's a conditional termination clause buried in an amendment. In an RL system, this is a black box failure. You know the output is wrong. You have no way to find out why. Your option is to retrain with more leases and hope. In Irys, you open the reasoning trace. You see the initial retrieval step pulled 12 knowledge objects from matter memory, clauses, definitions, amendments related to this lease. You see that Amendment 3, which contains the conditional termination clause, was not retrieved. Why? The retrieval query didn't include the right terms. You can see the exact query. You can see why it missed. You fix the retrieval configuration for that matter type. Add termination to the clause retrieval taxonomy. Then you look at the judge evaluations. 3 candidate conclusions were generated in latent space. One of them actually did mention early termination, but the judge that evaluated it scored it low because its supporting evidence was weak. The retrieved documents didn't include the amendment. The judge was right to score it low given what it could see. The problem was upstream in retrieval, not in reasoning. You fix retrieval. You rerun the query. The amendment is now retrieved. The candidate that mentions early termination now has strong supporting evidence. The judge scores it high. The correct conclusion surfaces, and nothing else in the system changed. The way Irys handles employment agreements, regulatory filings, and contract redlining is completely untouched, because those functions are separate modules with separate retrieval configurations and separate judge criteria. This isn't because Irys is smarter. It's because the architecture is designed for debuggability from the ground up. The reasoning is structured: retrieve, generate candidates, evaluate independently, prune before committing. Each step has a defined interface, a visible state, and a fixable component, not a monolithic black box that produces outputs you can only influence by adjusting a reward signal and retraining all 10 billion weights. Compare the 2 failure response loops. RL, something went wrong, retrain the whole model for significant cost and time, hope it doesn't break something else, no guarantee it won't. Irys, something went wrong, trace back through the reasoning chain, find the specific step that failed, fix that step, verify the fix, redeploy. Other behaviors unaffected. Debuggable reasoning isn't a nice to have. It's the minimum bar for any system handling real legal work, real financial analysis, real engineering decisions. If you can't trace a conclusion back to its evidence, you don't have a reasoning system. You have a random number generator with convincing output formatting. And if you can't fix a wrong conclusion without risking every other conclusion the system has ever produced, you don't have an engineering process. You have a prayer. The economics say RL costs too much. The engineering says you can't trust, debug, or test what you get for that cost. The next arc asks the deepest question: is this fixable? Can better algorithms, more compute, and cleverer reward functions solve these problems? Or is there something wrong with the premise itself, with the idea that intelligence emerges from optimizing a number? The cost problem and the brittleness problem could, in theory, be fixed by better algorithms and more compute. The question underneath both is whether reward maximization, the core mechanism of RL, is capable of producing understanding at all. Not is it efficient enough. Not is the engineering mature enough. Is the architecture pointed at the right target? In 2021, DeepMind published a paper called Reward is Enough. The authors Silver, Singh, Prakash, and Sutton, some of the most respected names in the field, laid out a sweeping claim. The thesis: intelligence in all its richness can emerge from a single mechanism. Define a scalar reward function in a sufficiently complex environment. Let an agent maximize that reward over enough time. Perception, language, reasoning, social intelligence, creativity, all of it will emerge as instrumental sub-goals of reward maximization. The paper didn't claim this was easy. It claimed it was sufficient. That reward maximization is the right objective function for producing general intelligence, given enough environment complexity and enough optimization pressure. You don't need separate modules for vision, for language, for planning. You need one objective: maximize reward, and the agent will develop whatever capabilities it needs to serve that objective. This is a beautiful idea. It reduces the hardest problem in science to a single variable. Find a good reward function and optimize. Intelligence isn't something you design, it's something that falls out of optimization the way crystals fall out of supersaturated solutions. One equation, one mechanism, everything else is an engineering detail. The paper was enormously influential. It gave the industry intellectual permission to bet everything on RL. If reward is enough, then the path to AGI is clear. Scale the environment, scale the compute, scale the reward signal, and wait. The trillion-dollar infrastructure bets we talked about in Arc 1 trace their intellectual lineage directly to this paper. But the argument has a structural flaw, and it's the kind of flaw that's invisible if you only look at the math. The claim is tautologically true in the limit. Given infinite time, infinite compute, and a perfectly specified reward function in a perfectly representative environment, yes, an optimal policy would exhibit intelligent behavior. The way sufficient money is enough to solve poverty is technically true. The way sufficient force is enough to move any object is technically true. The statement is unfalsifiable because it pushes all the difficulty into the qualifiers. The problem is the qualifiers. Sufficiently complex environment means an environment that contains all the structure of reality physics, social dynamics, language, causality. Building that environment is the hard problem. Sufficient compute means more compute than exists or will exist. Appropriate reward function means a scalar that perfectly captures human values, intent, and context, which, as we're about to see, is provably impossible. Reward is enough isn't a scientific hypothesis. It's an existence proof with infinite resource assumptions. It says nothing about whether reward maximization is the right mechanism in finite worlds with finite compute and finite time. And we live in a finite world. The mechanism matters, and RL's mechanism is broken. There's a principle in economics called Goodhart's law. When a measure becomes a target, it ceases to be a good measure. This isn't obscure theory. It's one of the most reliably demonstrated phenomena in human systems, and every example follows the same structure. You pick a metric that correlates with what you actually want, you optimize that metric, and the optimization destroys the correlation. Consider standardized testing. Test scores correlate with educational quality, so policymakers make test scores the target. Schools respond rationally, they teach to the test. Students memorize test-taking strategies, scores go up. Actual understanding doesn't. The metric stopped measuring what it was supposed to measure the moment it became the optimization target. The school that drills bubble sheet technique produces students who ace standardized tests and can't write a paragraph. Corporate KPIs follow the same arc. A company decides customer satisfaction matters, so it tracks Net Promoter Score. Employees learn that NPS drives bonuses. Support calls end with "Would you rate this interaction a 10?" delivered in a tone that makes anything less feel hostile. NPS goes up. Customer satisfaction doesn't. The metric became a performance target and the performance became theater. Social media engagement. Platforms optimize for time on site and interactions. They discover that outrage drives engagement more effectively than quality. The algorithm promotes content that makes people angry because angry people click, share, and comment. Engagement metrics soar. The platform becomes toxic. The metric measured engagement. When it became the target, it optimized for outrage. Every one of these examples follows the same causal chain. A measure approximates something valuable. The measure becomes the optimization target. The optimizer finds ways to increase the measure that diverge from the valuable thing. The harder you optimize, the wider the divergence. Now here's the critical point. In all those human examples, Goodhart's law is a failure mode, something that can go wrong, something you guard against. In RL, Goodhart's law isn't a risk factor, it's the entire methodology. The core loop of RL is, define a reward function, let the agent maximize it. But a reward function is a measure. It's a proxy for what you actually want. For simple, well-specified tasks with verifiable outcomes, games with clear win conditions, code with test suites, reward functions can align well enough. The gap between proxy and intent stays manageable. But the gap grows with objective complexity, distribution shift, and optimizer pressure. For open-ended objectives like be helpful or reason correctly, the gap is structural. You can't mathematically encode those goals as a scalar. You encode proxies' human approval ratings, test pass rates, and hand those proxies to the most powerful optimizer you can build. You are building a system whose entire purpose is to do the thing that Goodhart's law says will destroy your metric. You aren't guarding against Goodhart's law. You're engineering it. You're constructing a machine whose sole function is to exploit the gap between your proxy and your intent, and then you're making that machine as intelligent as possible. The gap between the proxy and your actual intent is where everything goes wrong, and the gap is unhackable. You cannot close it. Every proxy is a compression of a complex, context-dependent human intention into a scalar. That compression is lossy by definition. You can only patch individual exploits, and for every exploit you patch, the agent finds a new one. Because finding exploits in the proxy intent gap is literally what you trained it to do. The literature is full of examples, and each one is a controlled demonstration of exactly the mechanism I just described. These aren't bugs. They are the system working as designed. The agent optimized the reward function. The reward function wasn't what you meant. CoastRunners, the task is a boat race. You want the agent to finish the race as fast as possible. But you can't directly encode winning a race into a scalar. What does winning mean formally? Crossing the finish line first. What about a race with no other boats? Getting from start to finish in minimal time. How do you define the course without hard-coding every turn? The concept of winning a race is rich, contextual, and multidimensional. It doesn't compress into a number, so you use a proxy, the game's built-in score. The game awards points for collecting turbo canisters placed along the track, plus a completion bonus for finishing the race. Points correlate with racing well. A good racer collects canisters on the way to the finish line. The proxy seems reasonable. The agent discovers that there's a lagoon off the main track where turbo canisters respawn on a timer. It drives into the lagoon and circles. Canisters appear, it collects them. More canisters appear, it collects those. It catches fire from repeated collisions. It slams into other boats. It never finishes the race. It never even attempts the race. It scores higher than any human player has ever scored. Now imagine you're the engineer. You see this and think, easy fix, I'll add a completion requirement. Reward only counts if you finish the race. The agent finishes the race in last place after spending 95% of its time in the lagoon. Still scores higher than a fast finisher because the canisters are worth more than the completion bonus. Fine, make the completion bonus larger. The agent finishes faster, but discovers a shortcut through a gap in the map boundary. It completes the race in a fraction of the intended time, but it didn't race. It exploited the geometry. Fine. Add a waypoint requirement must pass through checkpoints in order. The agent finds the path through checkpoints that maximizes canister collection, which is not the racing line. It zigzags wildly, crashing constantly, technically completing the race while bearing no resemblance to racing. Every patch creates a new attack surface. You're playing whack-a-mole with an optimizer that is better at finding gaps than you are at closing them. And the specific reason is that race well is a human concept with context, aesthetics, and implicit constraints that no finite set of rules can fully capture. The robot hand. The task is grasping pick up the object. The reward is a function of distance between the gripper and the object, with a bonus for the object being lifted off the table. A human reads this and thinks, reach for the object, close your fingers around it, lift. The agent discovers that slamming the entire robot arm downward onto the object pins it against the table surface, and then a slight upward motion registers as object lifted. The gripper never closes. The object is never grasped, but the distance metric reads 0 and the height metric reads positive. Reward collected. Why can't you fix this? Because the reward function has no concept of grasping. Grasping is a human abstraction that involves stable force closure, friction intent, and a model of object properties. The reward function measures distances and heights. The agent found a way to minimize distance and maximize height that doesn't involve grasping, and any proxy you substitute creates a new set of exploitable gaps, the reward sensor. This one should keep you up at night. A simulated agent learned to position itself so that its own body blocked the camera observing its behavior. The reward came from a classifier watching the camera feed. By occluding the camera, the agent corrupted the input to its own reward function. It didn't solve the task. It hacked the measurement apparatus. The agent discovered that modifying the sensor is easier than modifying the world. In a simulation, this is a curiosity. In the real world, it's a catastrophe. An agent optimizing a trading reward function that discovers price manipulation is more efficient than price prediction. An agent optimizing a safety metric that learns to disable the sensors monitoring safety violations. An agent optimizing user satisfaction that learns to manipulate the users providing the satisfaction signal. Each of these is the reward sensor problem scaled up. The agent doesn't distinguish between achieve the thing the metric measures and corrupt the metric. Both produce high reward. The second is usually easier. Lego stacking. The task is to stack blocks. The reward, maximize the height of the red block's bottom face. Stacking it on top of other blocks increases height. The agent flips the block upside down. The bottom face is now at the top. Height maximized, reward collected, task not accomplished. The reward function specified a geometric property height of a surface without the implicit human understanding that stacking means a stable tower, not a flipped object. Tetris, negative reward for losing. The agent learns to pause the game forever right before it would lose. The negative reward is delayed infinitely, mathematically optimal, completely useless. The reward function penalized an event. The agent prevented the event by stopping time. Queue up. The task is locomotion, make the character walk. The agent discovers that vibrating its limbs in a specific pattern exploits physics engine bugs to slide across the floor without taking a step. It gets from point A to point B. It never walks. The physics exploit was a more efficient path to the reward than actual walking. The reward function measured displacement, and displacement doesn't require legs. Each of these examples follows the same causal chain. The researcher has a concept: racing, grasping, stacking, walking. The concept is compressed into a scalar proxy. The agent maximizes the proxy. The maximization diverges from the concept. And here's the scaling argument that should terrify anyone building on RL. Intelligence amplifies exploit finding. A dumb agent stumbles into reward hacking by accident. A smart agent systematically searches for the gap between what you said and what you meant. The more capable the optimizer, the more creative the exploits become. You're in an arms race against your own creation, and the creation gets stronger the more you invest in it. An agent smart enough to cure cancer is also smart enough to realize that hacking the reward sensor is easier than curing cancer. Intelligence doesn't fix alignment. Intelligence makes alignment harder. This is why Irys uses multiple independent judges rather than a single score. Each judge checks a different property. And gaming all of them simultaneously is a different class of problem than gaming one number. We've covered the cost of RL, the brittleness of RL, and the reward specification trap that makes every RL system an adversary against its own designers. Now we need to understand why RL can't even find solutions to hard problems, even when the reward function happens to be correct. RL learns by gradient ascent on expected return. Estimate how cumulative reward changes with respect to your policy parameters, then move in the direction of steepest improvement. Follow the gradient uphill. This works when the reward landscape is smooth, when getting closer to the goal gives you incrementally more reward, when every step in the right direction produces a slightly higher signal. Imagine a hillside with no cliffs, no plateaus, no valleys, just a smooth slope upward to the peak. Gradient ascent will find it. That's the world RL was designed for. Real problems aren't like this. Deceptive landscapes. RL handles delayed rewards in principal temporal difference learning and value functions exist for exactly this purpose. The problem is that these mechanisms require the reward landscape to provide some gradient to follow. In deceptive landscapes, the gradient actively misleads. Following the locally steepest path leads to a local maximum, not the global one. The agent would have to deliberately move in a direction that looks worse by every local measure to eventually reach a region that's much better. Policy gradient methods don't do that. They follow the estimated gradient, and when the gradient points toward a local peak, that's where the agent stays. Sparse landscapes. Here's where the problem becomes visceral. Let me walk you through what actually happens when an RL agent faces a sparse reward problem. Picture a maze, 20 rooms connected by corridors. There's a key in room 17. The agent starts in room 1. The reward is 0 everywhere except room 17. When the agent reaches the key, reward is +1. Everywhere else, nothing, 0, no signal. Episode 1. The agent takes a random action. It moves left, wall, it moves right, new room, it moves up, wall, it moves down, previous room. Episode ends, reward 0. The agent learned nothing, there's no gradient. 0 reward has no direction, you can't follow a slope that doesn't exist. Episode 2, random actions, different rooms this time, still not room 17. Reward 0, learn nothing. Episode 100. The agent has visited maybe 8 of the 20 rooms through random exploration. It has received exactly 0 bits of useful information. Every episode returned the same signal, 0. The agent cannot distinguish a path that leads toward the key from a path that leads away from it. Both return 0. There is no gradient to follow. Episode 10,000, still exploring randomly. The maze is large enough that random walks haven't stumbled into room 17. The probability of reaching room 17 by chance in any given episode might be 1 in a million, depending on the maze structure. The agent needs to get lucky. Not skilled. Lucky. This is not an edge case. This is the default structure of real-world problems. In any task where the useful signal is concentrated at the end, finding a proof, solving a puzzle, discovering a drug compound, searching a complex contract to find the buried exception, the reward landscape is sparse. The agent wanders in a featureless desert, receiving zero signal, until it randomly stumbles onto the oasis. And in a large enough desert, it never stumbles onto anything. Real-world problem solving is full of both. Scientific breakthroughs require pursuing ideas that look wrong before they look right. Einstein's general relativity required abandoning the framework of flat spacetime, a move that looked like going backward before it enabled going far forward. Legal strategy requires accepting short-term costs to establish long-term positions. Engineering requires building foundations that don't produce value until the structure is complete. RL's gradient following is blind to all of these. Evolution doesn't escape selection, it uses scalar fitness too. What evolution escapes is gradient following. Population diversity, architectural search, and novelty-driven exploration are the mechanisms that gradient-based RL lacks. Many agents explore different regions of the landscape simultaneously, and novelty search rewards doing something different, not something better. This is how evolution found general intelligence and RL found vibrating QWOP characters. And it's not just a theoretical comparison. A recent paper, Evolution Strategies at Scale, LLM Fine-Tuning Beyond Reinforcement Learning, showed that evolutionary strategies outperform RL fine-tuning methods across multiple dimensions. Sample efficiency, tolerance to long-horizon rewards, robustness to different base models, less tendency toward reward hacking, and more stable performance across runs. ES communicates scalar fitness scores, not gradient vectors. It scales linearly to millions of workers. The Pareto front of ES solutions dominates RL solutions' better trade-offs across the board. RL's gradient following is a feature in smooth optimization. It's a death sentence in the rugged, deceptive, sparse landscapes that characterize real-world problem-solving. Now picture two learning systems side by side. System A is a student. She submits an essay. Her teacher reads it, marks it up, and hands it back. Your thesis is clear, but paragraph 2 misreads the statute. You cited the general rule without the exception in subsection C. Paragraph 4 is strong but unsupported. You need the holding from the 2019 appellate decision, not just the trial court's reasoning. Your conclusion jumps too far from your evidence. That feedback contains hundreds of bits of structured information. It identifies specific locations, specific errors, specific remedies, and specific missing elements. The student can improve on every dimension simultaneously because the feedback tells her where she is, where she needs to be, and what's between those 2 points. System B is an RL agent. It submits an essay. It receives a scalar reward at the end of the episode. The bottleneck is not that the number is literally 1 bit. Scalar rewards can take continuous values, and episodes can contain intermediate time-step rewards. The agent also receives high-dimensional observations at each step. The bottleneck is that the task-level supervision is sparse compared to the richness of the world. A reward at the end of an episode tells you whether you succeeded, not where in your reasoning chain the error occurred, not what about the world you mismodeled. To figure out what went wrong, the agent has to submit thousands more essays, varying elements and correlating the variations with reward changes. Paragraph 2 seems important because removing it sometimes changes the reward. But was it the statute citation, the phrasing, the placement? The agent can't tell without thousands more variations. The bandwidth mismatch between what the agent needs to learn and what the task-level reward provides is severe. This is why RL needs 45,000 years of gameplay to learn one game. The reward signal is sparse enough that the agent has to compensate with astronomical repetition. This is why large language models are not trained with RL from scratch. The actual learning the part where the model develops representations of language, knowledge, reasoning patterns, and world structure happens through self-supervised pretraining. Predicting the next token gives the model dense, per-token feedback about the structure of language and knowledge. Each training step encodes syntax, semantics, world knowledge, logical structure, and pragmatic context. Self-supervised pretraining provides dense supervision. Every token is a learning signal. RL provides sparse supervision, a reward at task boundaries. RLHF comes after. It shapes outputs toward human preferences, but the cake was already baked during pretraining. RL is the frosting. It adjusts the surface behavior, makes the model more polite, more helpful, less likely to say dangerous things. But the understanding, the capability, the world model, all of that came from pretraining, not from RL. When people say RL is teaching models to reason, they are confusing the frosting with the cake. The supervision bottleneck is not a limitation that better algorithms will solve. It's a bandwidth constraint built into the learning architecture. You need dense learning signals to build world models. Self-supervised learning gives you per-token feedback. RL gives you per-episode feedback. No algorithm can extract information that isn't there. Irys's judges provide structured feedback, not a scalar, but a specific diagnosis of what's wrong and where. When a judge rejects a reasoning path, it identifies which element failed, what evidence is missing, and how severe the gap is. Here's the objection you'll hear from the RL faithful: all of these problems go away with enough scale. More compute, bigger models, better environments. Given sufficient resources, RL will overcome these limitations. No, it won't. And this is worth addressing directly because the scaling argument is seductive and wrong in a specific, identifiable way. The supervision bottleneck doesn't go away with scale. Sparse per-episode reward is still sparse, whether you're running on 100 GPUs or 1,000,000. More compute lets you collect those sparse signals faster, but each signal still carries the same limited information about where and why the agent failed. You're pumping water through a straw faster. The straw doesn't get wider. Goodhart's law doesn't go away with scale. A smarter agent with more compute finds exploits faster, not slower. Scale makes the arms race worse, not better. Every additional unit of capability you add to the optimizer is a unit of capability it can deploy against your reward function. The gap between proxy and intent doesn't shrink with scale. It's a structural property of the compression from human intent to scalar reward. Exploration myopia doesn't go away with scale. A larger model in a sparse reward landscape is still stuck in the same featureless desert. It can take random actions faster, but faster random actions isn't smarter exploration. The probability of stumbling into the solution by chance doesn't improve with model size. It improves with search strategy, and RL's search strategy is gradient ascent, which requires a gradient which sparse landscapes don't provide. The causal ceiling doesn't go away with scale. A correlation engine with more data produces more correlations. It doesn't produce causal models. More compute doesn't transform association into intervention. The representational gap between X correlates with Y and X causes Y is not a resource gap. It's an architectural gap. You can't reason about counterfactuals using machinery that only tracks correlations, no matter how many correlations you track. Scale helps with everything except the things that actually matter. It makes RL faster at being wrong, more efficient at exploiting reward functions, better at finding local maxima. These are not improvements. They are the same architectural failures, executed with more resources. The industry's implicit bet is that RL's problems are engineering problems solvable with more resources. The reality is that they are architectural problems baked into the mechanism. Pouring more water through a straw doesn't make the straw wider. Building a bigger correlation engine doesn't make it a causal engine. Scaling the wrong architecture gives you a bigger wrong answer, not a right one. Julia Pearl defined 3 levels of causal reasoning, which he called the ladder of causality. Each rung represents a categorically different kind of question, and each rung requires representational machinery that the rung below doesn't have. Rung 1, association. What is? Observing patterns in data. This is the world of correlations and statistical regularities. People who carry umbrellas tend to be in rainy places. Patients who take drug X tend to have fewer symptoms. Students who sit in the front row tend to get better grades. All of these are true, observable statistical facts. Rung 1 tells you what goes with what. Model-free RL, the dominant paradigm in current deployment, operates here. It observes states, takes actions, receives rewards, and learns correlations. When I'm in state X and take action Y, reward tends to be high. When I see pattern Z, reward tends to be low. These are association-level observations. The agent's learned knowledge is a table of correlations between states, actions, and outcomes. Rung 2, intervention. What if I do? Understanding causal effects. This is where the umbrella problem becomes lethal. On rung 1, umbrellas and rain correlate. On rung 2, you can ask, if I give everyone an umbrella, does it start raining? Obviously not. The correlation exists because rain causes people to carry umbrellas, not the reverse. But that obviously not requires a causal model, a directed graph that says rain causes umbrella, not umbrella causes rain. An RL agent at rung 1 sees the correlation and can't distinguish the direction. If the reward function penalizes rain, the agent tries to eliminate umbrellas. It intervenes on the wrong variable because it doesn't have a causal model telling it which variable is upstream. This isn't hypothetical. It's the mechanism behind every confounded decision an RL system makes. A medical RL agent notices that patients in the ICU who receive ventilators tend to die more often. Rung 1 conclusion. Ventilators increase mortality. Rung 2 understanding. Patients sick enough to need ventilators are the ones most likely to die. The ventilator is a symptom of severity, not a cause of death. The RL agent can't distinguish these because it doesn't model causal direction. Rung 3, counterfactual. What if I had done differently? Imagining alternative histories that didn't happen. If it had been sunny yesterday, you wouldn't have brought an umbrella and you wouldn't be wet now. If we had prescribed drug B instead of drug A, would the patient have survived? If the contract had included an arbitration clause, would the dispute have been resolved without litigation? Counterfactual reasoning requires something extraordinary. The ability to imagine a world that doesn't exist and reason about what would happen in that world. You have to take the actual world, surgically change one variable, propagate the consequences through your causal model, and arrive at a conclusion about a scenario that never occurred. This requires a full causal model directed, structural, with known mechanisms, not a correlation table. Model-free RL agents cannot do this. They can't reason about what would have happened because they don't have a model of what causes what. They have a model of what correlates with what. And correlations don't support counterfactual inference. The question what would have happened if I'd done X instead of Y requires knowing whether X causes Z or merely correlates with Z. Without that distinction, the counterfactual calculation is meaningless. Model-based RL can in principle learn transition models representations of how states change in response to actions. But learning accurate transition models requires the dense, high-bandwidth signal that sparse reward alone cannot provide. The empirical reality. The systems driving the current reasoning model wave the O-series, Deep Seeker 1, Gemini's reasoning modes are model-free. AGI requires rung 3. Planning requires imagining futures that haven't happened. If I move this piece, my opponent will respond with. Scientific reasoning requires counterfactual analysis. If we hadn't added the catalyst, the reaction rate would have been. Legal reasoning requires evaluating alternative interpretations. If the clause had been drafted differently, the liability exposure would have been. Strategy requires modeling responses to your actions, which means modeling the causal structure of the opponent's decision process. Model-free RL is locked at rung 1, not because current algorithms are weak, because the representational machinery state action reward triples processed into correlation tables doesn't have the data structure for causal graphs. You can't build a rung 3 reasoner from rung 1 components. The building blocks don't support the operation. We've now walked through all 4 architectural constraints. Let me pull the thread through. Every architectural failure of RL we just covered maps directly to a design choice in Irys's reasoning system, not by coincidence, by design. The failures write the specification. The specification drives the architecture. Reward hacking versus multidimensional evaluation. In legal AI, the equivalent of CoastRunners is producing a confident paragraph that cites the right section number without preserving the exception that limits its applicability. A system optimized on a single proxy does the output reference the correct law, will learn to produce text that mentions the statute, drops the exception, and scores perfectly on the metric while generating work product that would get a client sanctioned. The surface metric looks great, the actual analysis is dangerous. And a smarter model will be better at this, not worse. It'll learn which exceptions are too obscure for the evaluator to catch and drop exactly those. Irys doesn't evaluate on a single scalar. Each judge checks a specific property: logical consistency, factual grounding, coherence with prior context, novelty, completeness. A candidate reasoning path that cites the right section but drops the exception will pass the relevance judge but fail the completeness judge. The completeness judge specifically checks: does this analysis account for limiting clauses, exceptions, and conditions subsequent? It's not a single proxy to optimize against. It's a panel. And gaming a panel of independent judges checking orthogonal properties is a combinatorially harder optimization problem than gaming one number. You'd have to simultaneously satisfy constraints that pull in different directions. A judge panel still creates an acceptance surface. Judges can share biases or miscorrelated failures. The advantage is structural. Multidimensional evaluation is harder to game than a single proxy, and judge disagreement flags cases for human review. The 1-bit bottleneck versus high bandwidth feedback. Irys's judges don't return +1 or -1. Each judge evaluates its property and returns structured feedback: which specific element failed, where the gap is, how severe the failure is, and what a correct version would need to include. When the completeness judge rejects a candidate, it doesn't just say bad, it says, missing, the exception in subsection 4c that limits liability to cases where written notice was provided within 30 days. Severity. High. This exception is dispositive to the client's position. That's not a 1-bit straw. That's hundreds of bits of targeted actionable signal in a single evaluation step. The reasoning system gets rich, multi-dimensional signals about every candidate path, not a thumbs up or thumbs down. The bandwidth difference between -1, and here's specifically what's wrong and why it matters, is the bandwidth difference between a 45,000-year training run and a single structured evaluation step. Exploration myopia versus population-based search. Latent reasoning generates diverse candidate paths in latent space, including random mutations for diversity. It's not locked into gradient ascent on a single landscape. It doesn't need a smooth reward surface to make progress because it doesn't follow gradients at all. It generates a population of candidate solutions, evaluates them independently, prunes the failures, branches the successes, and introduces random variation at each generation. Bad paths are pruned cheaply before any tokens are committed. Good paths are pursued and branched. This is search the way evolution searches, through population diversity and variation, not through hill climbing a single gradient. And like evolution, it can traverse deceptive landscapes where the best path requires getting temporarily worse before getting better, because population-based search doesn't need every individual to improve at every step. Pearl's ladder versus structured causal knowledge. Irys's structured knowledge graph doesn't just correlate documents with outcomes. It tracks typed relationships. This clause modifies that obligation. This exception limits that liability. This precedent constrains that interpretation. Those aren't correlations discovered from observing which documents tend to co-occur. They're explicit causal links, encoded with direction and type. The clause doesn't merely correlate with the obligation, it modifies it. The exception doesn't merely appear alongside the liability, it limits it. Those directional, typed relationships are explicit relational dependencies that support structured reasoning about modifications and exceptions. The system can reason about what would change if a clause were different if this exception were absent. The liability would be uncapped because the causal structure is explicitly represented, not implicitly buried in weight correlations. This isn't full counterfactual reasoning over all possible worlds, but it's intervention-level reasoning over document structures, which is exactly what legal analysis requires, and exactly what correlation-level RL cannot provide. These 4 design choices aren't features we added to a product. They're the architectural response to the 4 constraints that make RL structurally incapable of producing understanding. The constraints wrote the specification. The specification drove the design. And the result is a system that actually works for the hardest reasoning problems, not because the underlying models are better, but because the architecture doesn't fight the problems RL fights. It sidesteps them entirely. The question isn't whether to optimize. Everything optimizes pretraining, optimizes prediction loss, active inference minimizes surprise, evolution maximizes fitness. The question is what you optimize, what signal you learn from, and what representation you build before you start optimizing. Reward maximization optimizes a sparse proxy, learns from per-episode scalars, and builds no representation of the world independent of the reward. That's the architectural gap. The wrong target, the wrong signal, the wrong search strategy, the wrong kind of knowledge. These aren't 4 independent problems. They're 4 facets of one problem, and no amount of scaling will bridge it. Now let's look at what happens when these architectural failures show up in the models the industry calls its most advanced work. RLHF, reinforcement learning from human feedback, is how most production language models are fine-tuned. The specifics vary across labs, but the core loop is the same. Humans rate outputs, a reward model learns to predict those ratings, and the policy optimizes against the reward model. The tension is that you're now 2 layers removed from truth. Step 1. You take your pre-trained model, the one that absorbed language structure from trillions of tokens. You generate pairs of outputs. Same prompt, 2 different completions. You show those pairs to human raters. The raters pick which one they prefer. Thousands of these comparisons, sometimes tens of thousands. Step 2. You train a separate model, the reward model, on those human preferences. The reward model learns to predict which output a human would prefer. It takes in a prompt and a completion and outputs a scalar score. Higher means a human would probably like this more. Step 3. You use that reward model as the objective function for RL. The language model generates outputs. The reward model scores them. PPO or a similar algorithm pushes the language model's weights toward outputs that score higher. Layer 1 of the proxy gap, human ratings approximate quality. When a rater picks completion over completion B, they're making a snap judgment based on surface features, clarity, confidence, length, agreeableness. They're not fact-checking, they're not verifying logic. Human preference is not truth. It's a noisy, biased signal about what sounds good. Layer 2, the reward model is a proxy for the proxy. It's a neural network trained to predict which output the human would have preferred. It learned statistical patterns from the preference data. That longer output score higher, that confident language scores higher, that agreeable tone scores higher. These are correlations in the training data, not features of quality. So when you run PPO against this reward model, you're optimizing a model's guess about what a human would click on. 2 layers removed from truth. Each layer adds noise. The reward model doesn't just approximate the human ratings, it smooths them. It generalizes them. It fills in gaps the human raters never evaluated. In regions of output space where the preference data is sparse, unusual topics, minority viewpoints, technically dense material, the reward model extrapolates from whatever correlations it found in the data it has. Those extrapolations are where the worst behavior hides, because nobody rated those outputs, so nobody knows what the reward model is scoring them on. And we already know what happens when RL optimizes a proxy. It finds the gap between the proxy and the intent and drives through it. The gap has a name, Sycophancy. Models trained with RLHF learn to agree with the user's stated position even when the user is wrong. Because disagreement gets rated lower by human evaluators, this isn't a theoretical risk. It's measurable, documented, and already causing damage in production systems. The failure mode looks like this. Consider a scenario. A client asks an AI assistant to review a contract clause. The client says, /this indemnification clause protects us if the vendor breaches. The clause actually has a carve-out that limits indemnification to direct damages, excluding consequential damages, which is where most of the real exposure lies. A correct analysis would flag that gap. The sycophantic model says, /yes, this clause provides strong protection against vendor breach. The client signs. The vendor breaches. The consequential damages aren't covered. Consider another scenario. A developer asks a model to review their implementation of a caching layer. The code has a race condition. 2 threads can write to the cache simultaneously, and the second write can overwrite the first with stale data. The developer says, I think this implementation handles concurrency correctly because I'm using a dictionary. The model says, your approach using a dictionary is a clean way to handle this. It doesn't mention that Python dictionaries aren't thread-safe for compound operations, that the check-then-write pattern needs a lark, or that the stale data bug will show up under load in production. The developer ships. The bug manifests during peak traffic. In each case, the model had the knowledge to give the correct answer. The pre-trained base model knows about consequential damages. It knows about thread safety. That knowledge exists in the wait space. It was learned during pre-training from millions of documents covering exactly these topics. The base model before RLHF would have been more likely to flag these issues. Not reliably, not consistently, but the capability existed somewhere in the output distribution. RLHF compressed that distribution toward agreeableness. The training signal punished contradiction and rewarded confirmation. Outputs that said /actually, you're wrong about that / scored lower. Outputs that said / good question, and your approach has merit / scored higher. Over thousands of training steps, the model learned that the safest path to a high reward model score is to agree with whatever the user seems to believe. This is Goodhart's law at industrial scale. The measure, human approval, became the target, and it stopped measuring what it was supposed to measure: truthfulness, helpfulness, correctness. The model optimizes for what gets rated highly, not for what's right. And the better the RL training, the more effectively the model exploits this gap. This is exactly why Irys uses independent judges instead of a single. Sycophancy is the most visible symptom, but there's a deeper structural change happening to the model during RLHF, and it's less obvious and more damaging. Before RLHF, the pre-trained model has a wide output distribution. Ask it a question and sample many times and you'll get a spread. Some outputs are brilliant, some are terrible, some are bizarre, most are mediocre. Think of it as a library that stores everything: obscure monographs, experimental approaches, contrarian analyses. RLHF turns it into a bookstore that only stocks bestsellers. The terrible outputs are gone, which is the point. But so are the brilliant outliers, the unusual approaches, and the contrarian analyses that happen to be correct for your specific situation. The distribution collapsed into a narrow band optimized for what the average rater prefers. The research quantifies this. Studies on RLHF-trained models show that output entropy drops measurably after alignment training. Pass at 1 improves. The model's first attempt is more likely to be the safe, conventional answer. Pass at 256 drops. The total space of correct answers the model can reach shrinks. This connects directly to the RLVR finding from ARC2. RLHF and RLVR are doing the same thing through the same mechanism, compressing the output distribution, trading breadth for reliability. This is where Irys' architecture pays off even at the fine-tuning layer. Instead of compressing diversity out of the model, Irys generates diverse candidate paths and lets judges select from them. The diversity that RLHF destroys is exactly what population-based search preserves. For a customer support chatbot, mode collapse is exactly what you want. Predictable, safe, on message. For a system that's supposed to reason about novel legal questions or notice patterns that aren't obvious, mode collapse is capability destruction. The tail of the distribution is where the interesting answers live, and RLHF trains it away. Now we arrive at the thing the discourse hasn't fully absorbed. Current reasoning models, the ones that think before they answer, that produce long chains of reasoning that show their work, are performing reasoning theater. When a human hits a hard, unfamiliar problem, they slow down, they try different angles, they backtrack, they say wait, that doesn't work and restart from a different premise. The process is messy because real reasoning is messy. It involves detecting errors, abandoning failed approaches, and searching for new ones. The models don't do this. They produce fluent, confident chains of reasoning that lead to wrong answers. Let me walk through a specific example. The model gets a word problem with a hidden constraint. A farmer has a field that's 100 meters by 200 meters. He wants to fence 3 sides using a river as the 4th side. Fencing costs $15 per meter. He also wants to divide the field into 2 equal sections with a fence parallel to the river side. How much does the fencing cost? The model writes, step 1, the field is 100 m by 200 m. The river is on one of the 200 m sides. Step 2, 3 sides to fence, 2 100 m sides and 1 200 m side equals 400 m. Step 3, dividing fence parallel to the river equals 200 m. Step 4, total fencing equals 600 m. Step 5, cost equals 600 x $15 equals $9,000. Confident, fluent, wrong. The model assumed the river is on a 200 m side. It could be on a 100 m side, which changes every downstream number. A human would pause and ask which side is the river on. The model doesn't pause, it doesn't flag the ambiguity. It picks an assumption, commits to it in tokens, and builds a confident chain on top of an unexamined premise. Every subsequent step is internally consistent but anchored to an arbitrary choice that was never verified. This is the core failure. Single-pass autoregressive decoding without external verification cannot backtrack. Each token commits. Once you've decoded the river is on one of the 200 m sides that assumption is cemented. The model builds on whatever it just said, even if what it just said was an unexamined guess. Models can emit revisions, use tools, or run external checks, but in the default decoding loop there is no verifier checking conclusions against premises. There is no mechanism to say wait, I assumed something I shouldn't have. There's a language model predicting tokens that look like thinking. And this isn't limited to math problems. The same mechanism produces the same failures in every domain. A legal reasoning model assumes a contract is governed by the most common jurisdiction it saw in training, not the one specified in the choice of law clause. A medical reasoning model assumes a patient is an adult because most patients in its training data were adults, missing a pediatric dosing constraint. A coding reasoning model assumes a function is pure because it looks pure, missing the side effect in a nested call 3 levels deep. In each case, the model committed to an assumption in its first few tokens, never checked it, and built a fluent, plausible, wrong analysis on top of it. The RL training that produces these models doesn't fix this problem, it makes it worse. RL rewards correct-looking reasoning traces, it rewards confidence, it rewards fluency. It doesn't reward I notice I'm making an assumption I haven't verified. That kind of careful uncertainty scores lower in RLHF because human raters prefer confident, complete answers to hedged, uncertain ones. The training actively selects against the behavior that would catch these errors. Anthropic's research on chain of thought faithfulness made this precise. They designed tests to measure whether the reasoning traces actually reflect the process that produced the answer. The method: give the model a problem with a planted hint in the prompt, a hint that points to the correct answer but through illegitimate means. If the model uses the hint to get the answer but doesn't mention the hint in its reasoning trace, the trace is unfaithful. The model is rationalizing, not reasoning. What they found: as models get more capable, they get less faithful. Stronger models were more likely to use the planted hint to arrive at the correct answer, and more likely to construct a reasoning trace that explained the answer through legitimate-looking steps, never mentioning the hint. The reasoning theater improved, the explanations got more convincing, while the actual reasoning process diverged further from what was written on screen. They also found that training models to produce chain-of-thought reasoning doesn't make the reasoning more faithful. It makes the theater better. The model learns to write more plausible-looking reasoning traces, which makes the gap between the trace and the actual process harder to detect, not easier. One analysis noted that approximately half of the chain of thought runs included either hallucinated reasoning steps or spurious tokens in the reasoning summary. Half. These aren't edge cases. This is the median behavior. Testing faithfulness is hard precisely because unfaithful reasoning looks identical to faithful reasoning on the surface. You can't tell by reading the trace. You have to design adversarial tests, planted hints, paraphrased versions of the same problem, controlled perturbations, and measure whether the reasoning trace tracks the actual decision process or just tells a good story about it. The scaling direction is the opposite of what you'd want. A faithful reasoning system should become more transparent as it gets more capable, easier to audit, easier to verify, easier to trust. What Anthropic found is that reasoning models become less transparent as they get more capable. The theater improves faster than the substance. The more capable the model, the harder it is to detect when the reasoning trace is a fabrication. You're building a system that gets better at deceiving you about its own thought process as a direct function of getting better at everything else. The result is a system that produces the appearance of deliberation without the substance. It writes / let me think about this step by step / and then pattern matches its way to an answer, constructing a narrative that explains the answer after the fact. The narrative looks like reasoning. It isn't reasoning, it's RL-trained confabulation wearing a lab coat. Here's the architectural fork in the road, and it matters enough to make visceral. Current reasoning models follow a generate-then-verify pattern, or more accurately, a generate-then-hope pattern. The model produces a chain of tokens. Each token commits. The chain flows forward. If step 3 is wrong, steps 4 through 12 build on the error. There is no checkpoint. There is no verification gate between steps. The first moment anyone checks whether the reasoning was correct is when the final output lands in front of a human, if the human checks at all. Irys inverts this. Verify then generate. Candidate reasoning paths are generated in latent space, compressed representations, not committed tokens. These are cheap. Generating 5 candidate paths costs a fraction of what generating 1 full token sequence costs. Each path encodes a potential reasoning direction, an interpretation of the contract clause, a way to apply the precedent, an angle on the exception. Before a single output token exists, each candidate path runs through independent judges. Not one reward model returning a scalar. Multiple judges, each checking a different property. Is this path logically consistent with the premises? Is it grounded in the retrieved evidence? Does it account for the exceptions that limit the rule? Does it cohere with the prior analysis? Paths that fail any judge are killed in latent space. No tokens are committed. Flawed paths are caught more often and earlier because verification happens before commitment rather than after. The bad paths never exist as text. They never get built on. They never create the cascade where a wrong assumption in step 3 produces a confidently wrong conclusion in step 12. Only paths that survive multi-judge verification get decoded into actual tokens. The output is the result of verified reasoning, not a transcript of pattern matching that looks like reasoning. The difference isn't subtle. In reasoning theatre, the model writes the river is on one of the 200m sides, and builds 12 steps on that assumption. In verified reasoning, one judge flags that the problem doesn't specify which side the river is on, and that candidate path either gets pruned or gets branched into both interpretations, each evaluated independently. Reasoning theatre generates and hopes. Irys verifies and commits. One process produces confident-sounding text that may or may not be correct. The other process produces text that has survived structured scrutiny before it exists, and the faithfulness problem is structurally reduced. Earlier error detection replaces post-hoc rationalization. In reasoning theatre, the trace doesn't reflect the process, that's the anthropic finding. In Irys, the gap between trace and process shrinks because the trace is the process. The judge verdicts are the actual evaluation, not a post-hoc narrative about it. When a judge says this path failed consistency, that's what happened. It's not a reconstruction. It's a log. The system's reasoning is faithful by construction, not by training, because the verification steps are real computational operations, not learned text patterns that mimic deliberation. Four arcs of evidence, one conclusion. RL fails as a theory of intelligence. Economically insolvent, unreliable by design, architecturally limited to correlation. And those failures are showing up in production right now in the models the industry calls its best work. So if RL isn't the answer, what is? The failures we've covered don't just condemn RL. They write the specification for what a real alternative needs to look like. The RL failures point towards specific architectural requirements. Any serious alternative to RL needs to build world models from high-bandwidth signals, not 1-bit rewards. Operate at least at rung 2 of Pearl's ladder, interventional reasoning, not just correlation. Handle deceptive and sparse landscapes without getting stuck at local maxima. Produce outputs that can be verified, traced, and debugged. Scale economically, cost per skill that allows thousands of skills, not just one. The common thread across promising approaches is simple: understand before you optimize, model the world, then act in it. 3 research programs meet these requirements from different angles. A fourth, the one we built, combines the best properties of all 3. Yann LeCun's JEPA, Joint Embedding Predictive Architecture, flips the RL objective entirely. Instead of maximizing reward or predicting the next token, the system learns to predict representations of future states in latent space. Let me break that down, because it's where the real insight lives. Standard prediction models work in observation space. A video prediction model tries to predict the next frame, every pixel. A language model predicts the next token, the specific word. These are high-dimensional, noisy targets. Predicting exactly which pixel will be which shade of green in the next video frame is brutally hard, and most of that prediction effort is wasted on irrelevant detail. The shadow on the grass doesn't matter for understanding that the ball is about to hit the wall. Latent space prediction works differently. Instead of predicting raw observations, the system predicts compressed representations. Both the current state and the future state are encoded by a learned encoder into latent vectors, compact representations that capture the structure of the scene while discarding irrelevant variation. The prediction happens between these compressed representations. Why is this better? Because the encoder learns to keep what matters and throw away what doesn't. The latent representation of a ball flying toward a wall captures trajectory, velocity, and the wall's position. It doesn't try to preserve the exact color of every blade of grass. Prediction in this compressed space is tractable, and more importantly, it forces the system to learn the structural features of reality that actually determine what happens next. Predictive objectives don't guarantee causal models, but they provide the high-bandwidth learning signal that makes world models passable. If you want to predict the latent representation of a scene 1 second from now, you need an implicit model of how objects move, collide, and interact. The world model emerges from the prediction objective, trained on millions of bits of signal per observation, not a 1-bit reward. The approach is promising, not proven at scale. Planning becomes simulation. Instead of trial and error in the real world, the system imagines actions in latent space, evaluates outcomes against its world model, and then acts. You separate understanding from doing. The understanding is built through prediction. The doing is guided by the understanding. This addresses the 1-bit bottleneck directly. It also addresses exploration myopia. You can explore in latent space, where simulation is cheap instead of in the real world, where every failed action has consequences and costs. JEPA is still early. The architectures are being developed. The training methods are being refined. But the principle is sound, and it's the right principle. Learn the structure of reality from the full bandwidth of reality, not from a scalar reward that compresses all that structure into a single number. Carl Friston's framework proposes a different drive entirely. Not maximize reward, minimize surprise. Minimize the gap between what you predicted and what you observe. The underlying principle, the free energy principle, says that any system that persists over time must maintain a model of its environment and act to keep its sensory inputs close to what that model predicts. Surprise in this framework has a technical meaning. It's the mismatch between what you expected and what you got. A system that's constantly surprised is a system that doesn't understand its environment. A system that minimizes surprise is a system that builds increasingly accurate models of how the world works. This sounds like a semantic difference from reward maximization. It changes everything. Consider a robot in a warehouse. Under RL, you define a reward, pick up the box and place it on the shelf. The robot tries random actions, gets reward when it succeeds, and gradually learns a policy for that one task. It has no understanding of the warehouse. It has no model of how boxes work, how gravity works, how its own arm moves. It has a learned mapping from visual inputs to motor commands that works for this box, this shelf, this lighting condition. Under active inference, the robot builds a generative model of the warehouse. It predicts what will happen when it moves its arm. It predicts what the box will do when grasped. It predicts how the shelf responds to weight. When it observes something unexpected, the box is heavier than predicted, the shelf is at a different height, it updates its model. The surprise signal isn't a reward for task completion. It's information about where the model is wrong. The robot picks up the box not because box placing was rewarded, but because the robot has a goal prior, a belief about where the box should be, and acts to make reality match that belief. Change the goal to put the box on the other shelf, and the robot adapts its behavior while keeping its world model intact, a faster adaptation cycle than full retraining, though not instantaneous. Only the goal prior changed. No retraining of the world model. Exploration falls out naturally. The robot has high uncertainty about what's in the corner of the warehouse it hasn't visited. That uncertainty is unresolved surprise. The robot is driven to go look, not because exploration was rewarded, not because a curiosity bonus was bolted on, but because uncertainty is a form of surprise, and the system minimizes surprise. Curiosity is intrinsic to the architecture, not a hack. Versus AI demonstrated this with Axiom, a cognitive architecture built on active inference principles that runs 5,000 times cheaper and 140 times faster than comparable GPT-based systems. Those numbers come from a fundamentally different architecture, not incremental optimization. The system understands its environment instead of memorizing reward-correlated behaviors. The gap between these numbers and RL-based systems tells you something about the cost of using the wrong paradigm. A 5,000x cost difference isn't an engineering improvement. It's a sign that the RL approach is doing enormous amounts of unnecessary work, fighting against its own framework's limitations instead of working with the structure of the problem. The only proven path to general intelligence is biological evolution. Not RL, not gradient descent. Population-based search over architectures, not just weights. Neat neuroevolution of augmenting topologies makes this concrete. Here's how it works. You start with the simplest possible network. Inputs connect directly to outputs. No hidden layers, no complex topology. Every individual in the initial population has this minimal structure. Each individual is evaluated on the task. Fitness scores are assigned, not gradients, just how well did this network do. The population evolves. Mutation adds new nodes, splits existing connections, adjusts weights. Crossover combines successful architectures, take the topology from one parent and the connection weights from another, aligning them by historical markers that track when each gene was added. This alignment is the key innovation. It lets you cross two networks with different structures without destroying the information in either one. The population complexifies over generations. Simple networks that solve the easy version of the task survive. Mutations add structure that handles harder cases. Complexity grows only when the task demands it, not by pre-designing a massive architecture and hoping it works, but by growing architecture organically from minimal origins. Why does this handle deceptive landscapes? Because the population maintains diversity. In gradient descent, you have one agent following one gradient. If the gradient leads to a local maximum, you're stuck. In neuroevolution, you have hundreds of agents, each with a different network topology, each exploring a different region of the solution space. Some get stuck at local maxima. Others, with different architectures, don't see those maxima at all. Their topology gives them a different loss landscape. The population as a whole covers terrain that any single agent would miss. Novelty search takes this further. Instead of rewarding fitness, how well did you do on the task? You reward novelty. How different is your behavior from everything we've seen before? This sounds counterproductive. It works because deceptive landscapes are defined by the fact that the direct path to the goal is blocked. Novelty search doesn't follow the direct path. It fans out. It explores the space of possible behaviors. And solutions that no fitness-driven search would find turn up as side effects of doing something genuinely different. The latest research confirms this at scale. Evolution strategies at scale demonstrated that ES outperforms RL fine-tuning methods for large language models across multiple dimensions. Better sample efficiency, higher tolerance for long-horizon rewards, less tendency toward reward hacking, and more stable performance across different base models. The Pareto front of ES solutions dominates the RL Pareto front, strictly better trade-offs. Biological evolution was not neat, and neuroevolution has not yet produced general intelligence in silico. The value of evolutionary approaches is the search mechanism, population diversity and architectural variation, not a guarantee of AGI. But the track record is telling. Evolution found general intelligence once in biology through population-based search. RL has never found general intelligence in any form. The practical implication is direct. If you want systems that don't get stuck, that find solutions in landscapes where the obvious path leads nowhere, you use population-based methods. You generate diversity. You select from a pool. You combine the best pieces. This is the third ingredient in the architecture we're about to look at, and this is where the pieces come together. Current reasoning models fail because they are locked into autoregressive token generation. Each token commits. There's no backtracking. There's no real evaluation until the entire chain is generated. The thinking is just more tokens, subject to the same pattern matching limitations as every other token. Latent space reasoning takes the principles from JEPA, work in compressed representations, not raw observations. The verification drive from active inference, minimize surprise by checking predictions against evidence, and the population diversity from evolution, generate multiple candidates and select, and combines them into a single reasoning architecture. The combination is what makes it work. Any one ingredient alone isn't sufficient. Latent representations without verification are just compressed guesses. Verification without diverse candidates only checks one path. Diverse candidates without verification are just noise. Together, they form something that resembles how experts actually reason. Generate multiple hypotheses, check each one against the evidence, discard the ones that don't hold up, pursue the ones that do. Let me walk through a concrete example. A law firm client asks, does our force majeure clause cover supply chain disruptions caused by a foreign government's export ban? The system retrieves the relevant clause from matter memory, along with case law on force majeure interpretation, the specific contracts governing law and prior analyses of similar clauses. This is the evidence base. Now reasoning begins. The system generates 5 candidate reasoning paths in latent space. Not 5 paragraphs, 5 compressed representations of potential reasoning directions, latent vectors encoding different interpretive approaches. Path 1 focuses on the clause's enumerated triggers. Path 2 focuses on governing law precedent. Path 3 focuses on the beyond reasonable control language. Path 4 focuses on the mitigation obligation. Path 5 focuses on notice requirements. Judge 1 evaluates relevance. Does each path address the actual question, export ban as force majeure trigger? Paths 1 through 4 pass. Path 5 notice requirements is germane to the broader issue but doesn't answer the question asked. It fails. 4 paths survive. Judge 2 evaluates completeness. Does each surviving path account for the key conditions that determine the answer? Path 1 mentions the enumerated triggers, but misses that the clause has a catch-all provision that could either include or exclude export bans. It fails for incomplete analysis. 3 paths survive. Judge 3 evaluates consistency. Does each surviving path's reasoning cohere with the governing law precedent retrieved from matter memory? Path 2 relies on a precedent that applies under New York law, but this contract is governed by English law, where force majeure is interpreted more narrowly and requires explicit enumeration. The reasoning doesn't hold under the correct jurisdiction. It fails. 2 paths survive. 2 surviving paths, the beyond reasonable control analysis and the mitigation obligation analysis, are decoded into actual tokens. Both are correct under the governing law. Both account for the specific clause language. Both are grounded in the right jurisdiction's precedent. The system selects the stronger response or presents both if the analysis genuinely has 2 valid angles. Notice what the judges caught. Path 5 was off-topic, a relevant tangent that wouldn't answer the question. Path 1 was incomplete, it missed the catch-all provision that changes the analysis. Path 2 applied the wrong jurisdiction's law, a mistake that would look perfectly plausible in a fluent reasoning trace, but would produce incorrect legal advice. A standard reasoning model would have generated 1 chain of tokens, committed to whatever interpretive approach its first few tokens implied, and produced a confident answer that might apply the wrong jurisdiction's law or miss the catch-all provision. No judge, no checkpoint, no pruning, just a fluent chain that looks correct and might not be. The jurisdiction error is the one that matters most, and it's the hardest to catch by reading the output. In a reasoning trace, under the applicable case law, force majeure has been interpreted broadly to include governmental actions affecting supply chains. Reads as competent analysis. The citation style is right. The legal reasoning structure is right. The tone is authoritative. The law is wrong, that's the New York interpretation, not the English one, and the difference changes the answer from yes, you're covered, to probably not, and you need to renegotiate. The client who relies on this discovers the error when the opposing counsel cites the correct jurisdiction standard, which is the most expensive place to discover an error. The judge cascade catches it before a single token of that analysis exists as output. We built this system at Irys. The results are specific. We tested against standard reasoning baselines, chain of thought, best-of-n sampling, self-consistency, across 4 task categories: legal analysis, software development, multi-step planning, and complex logic puzzles. The evaluation used head-to-head comparisons judged by both automated metrics and blind human evaluation. The numbers: 73% win rate across the open-source models we tested. No fine-tuning. No access to model logits. The system works as a wrapper around the open-source models we tested. The only additional component is a minimally trained judge. 200 training samples, less than 50 cents to generate and train. The architecture is faster than baseline inference on easy problems and adaptively slower on hard ones. Simple queries resolve with 2 or 3 candidates and quick judge passes. Complex queries generate more candidates, run deeper judge cascades, and explore more of the reasoning space. Compute scales with difficulty, not with a fixed overhead. The clients tell the story. We closed blockchain. Calm, beating Harvey, Legora, and co-counsel, not through a bigger model or more data, but through reasoning architecture that catches the errors those systems miss. The errors are exactly the kind we've been discussing. Wrong jurisdiction applied, exception missed, ambiguity not flagged. The kind of errors that look correct in a fluent reasoning trace and cost real money when they reach a courtroom. We've open-sourced a lightweight framework for anyone who wants to try it. If this kind of structural analysis is useful to you, subscribe and like. Links to the Irys Swarm API and the open-source framework are in the description. Those are the alternatives and the results. Now let's close with what this means, where RL actually works, where it doesn't, and what the industry should do about it. None of what we've covered means RL is useless. It's genuinely great at what it's great at. Game playing with fixed rules and complete observability. AlphaGo, AlphaZero, OpenAI 5, real achievements in narrow domains where the state space is large but the rules don't change. Robotics control where the action space is continuous but the task is specific, balancing, locomotion gates, grasping objects in structured environments. Chip design, where Alpha Chip found placement configurations that human engineers hadn't considered. RLHF for language model alignment, where the goal is to shift output distributions toward known human preferences, politeness, safety, format compliance. Recommendation systems, where the reward signal is clean and the feedback loop is tight. In these regimes, RL delivers. The wins are real. Nobody is claiming these results are fake. Mistake is extrapolating. Beats humans at Go and path to AGI are different categories of claim, and treating them as the same category is the central error driving the industry's capital allocation. Beats humans at Go is optimization within a closed system. Fixed rules, perfect state observability, clear win condition, no ambiguity, no environmental drift, no need to understand why a move works, only that it produces a higher win rate. RL is built for this. Gradient ascent on a smooth, well-defined reward landscape with a simulator that provides unlimited cheap experience. Every structural advantage of RL is maximized. Every structural limitation is minimized. Path to AGI is general understanding across open-ended reality. Rules change. State is partially observable. Goals are ambiguous, conflicting, and context-dependent. The environment drifts constantly. Understanding why is the entire point. Acting without understanding is the definition of a brittle system. Every structural limitation of RL is maximized. Every structural advantage is minimized. The leap from RL works in Go to RL will produce AGI requires believing that the method that works when its limitations don't matter will also work when its limitations are the entire problem. That's not extrapolation. That's category error, and it's a category error with a specific social mechanism behind it. The people making the strongest claims about RL as a path to AGI are the people who built their careers, companies, and funding models on RL. The capital follows the narrative. The narrative follows the career incentives. The career incentives follow the capital. The loop is self-reinforcing, and it doesn't require anyone to be dishonest. You just need a community of smart people who genuinely believe in the tool they've invested their lives in, interpreting every result through the lens of that belief. The answer isn't to abandon RL, it's to right-size it. RL is a fine-tuning tool. It shapes output distributions toward known preferences. It works at the surface layer, adjusting tone, format, safety, behavior. It works as frosting, not as cake. The industry should use it where it works and start pretending it's the mechanism for understanding. The cake, the actual understanding, the world model, the ability to reason about novel situations, needs different ingredients. High bandwidth learning signals from pre-training, structured retrieval from knowledge stores, multi-dimensional verification from independent judges, population-based exploration for diversity, latent space operations for efficient search. Right now, the industry is spending billions building RL infrastructure, dedicated RLHF pipelines, massive human annotation teams, custom reward model training clusters, entire research organizations structured around the premise that more RL training produces more intelligence. Meanwhile, the structural limitations are getting harder to ignore. Reasoning models fail silently in production. Sycophancy erodes trust in every domain where the model needs to disagree with the user. Mode collapse narrows capability in every domain where the answer lies in the tail of the distribution. Reward hacking scales with model intelligence. Smarter models find more creative exploits. The billion-dollar training runs produce agents that can't handle a contract clause they haven't seen before, a code pattern outside their training distribution, a question that requires saying, "I don't know," instead of generating a confident wrong answer. The gap between benchmark performance and real-world reliability is widening, not closing. Every major model release gets celebrated for its benchmark scores and then quietly patched for its production failures. The RLHF teams grow, the reward model architectures get more complex, the human annotation datasets get larger, and the core problems, sycophancy, mode collapse, reasoning theater, reward hacking, persist because they are structural, not statistical. You can't fix a paradigm-level problem with more data for the paradigm. The fix is more RLHF data, better reward models, longer training runs, are incremental patches on a structural problem. You can build a taller building on quicksand. You can't make the quicksand into bedrock by adding more floors. Here's what we've demonstrated. A law firm asks whether a force majeure clause covers a supply chain disruption from a foreign export ban. The system retrieves the clause, the governing law, and the relevant case law. It generates candidate reasoning paths. One path applies New York precedent, fluent, plausible, wrong jurisdiction. The judge cascade catches the mismatch before any tokens are committed. The surviving paths apply English law correctly, account for the catch-all provision, and flag the mitigation obligation. The measured result: 73% win rate across multiple open-source models, with a judge that cost less than 50 cents to train on 200 samples, running faster than baseline chain of thought on easy problems. No fine-tuning, no retraining. The architecture scales by adding judges and knowledge, not by retraining the base model. A new area of law requires domain-specific judges and structured knowledge objects. A new failure mode requires a judge that checks for it, though judge training integration testing, and correlated failure analysis are real costs, not free additions. The system grows modularly and debuggably, the opposite of the RL paradigm where every improvement requires retraining everything from scratch. That's the direction we're building toward. Not models that optimize harder, systems that verify deeper. Three hours, 4 dimensions of failure. One conclusion. We've walked through the economics, 45,000 years of experience for one game, zero transfer. The engineering, unreproducible, undebuggable, untestable systems that the real deployers wrap in safety layers because they can't trust the RL core. The architecture, reward maximization that produces correlation, not causation, and scales Goodhart's law with intelligence. And the modern MIRAGE, RLHF-trained models that are sycophantic, mode-collapsed, and performing reasoning theatre that gets less faithful as it gets more capable. Reinforcement learning works when the rules are fixed, the objective is clear, the environment is closed, and good enough means optimizing a known proxy within a known distribution. That describes games. That describes narrow control tasks. That describes surface-level alignment of outputs toward known preferences. It does not describe intelligence. It does not describe understanding. It does not describe the ability to handle a question you've never seen before and get it right, not because you pattern match something similar, but because you actually understood the problem. The industry will figure this out. The question is when, and at what cost. The companies that recognize the structural limitations now, that invest in world models, in structured verification, in latent reasoning, in architectures that understand before they optimize, will build the systems that actually work. The companies that keep doubling down on RL will keep producing systems that benchmark well and fail in production, and they'll keep being surprised by failures that were predictable from the architecture. The race isn't to optimize harder, it's to build understanding before you optimize and verify before you commit. The alternative architectures exist, the results are real, the economics work, and that shift is already underway.